The following message is best viewed on an oscilloscope.
Okay, let's start. Hello, everyone. Welcome to the first neutrino session of ICHEP 2020. So we have already above 100 participants in our session. I see 116 participants, and we have an interesting program. So let's start. We have talks we do 13 minutes or 12 minutes talk and then 3 minutes question. So if you want to ask a question, please use the raise hand sign, and then you will get permission to talk. But please try to be brief because we have only short time for questions. And there's also the possibility to use the chat tool for additional questions. So let's start with the first talk. We have Mariam Tortola about global fields to neutrino mass and mixing. So please, Mariam, if you start sharing your screen.
Yes.
Start.
Okay, can you see my screen?
Yes, we see your screen.
Okay, thank you, Thomas. Okay, so thanks everybody for attending this talk. So here I will try to summarize what is the current status of global fits to neutrino masses and mixings. Here is the outline of this short talk. Well, I will restrict myself to the standard 3 neutrino framework, and I will discuss the results presented in this paper we uploaded to the archive 1 month ago. Also, you can find the figures and the chi-square tables from this analysis in our website here, and also you can find similar works made by other groups like the NuFit collaboration or the Valle group. Here you have the references. And since our analysis was published just before the Neutrino conference, we have included only the data available before. But in any case, we are working on the update of including this new data, and I will discuss some of the new results presented in the Neutrino conference and how they can affect the global analysis. So I guess all the people in the audience is familiar with this formalism of neutrino, 3-flavor neutrino picture. So essentially, we will parameterize the mixing matrix in terms of 3 mixing angles and 1 CP phase relevant for neutrino oscillations. And also, we will have 2 other parameters, the mass splittings 2-1 and 3-1, proof that solar and atmospheric experiments. And also, we know so far the sign of the solar mass splitting delta M21, but current data gives not enough information to know the sign of delta M31. So far we have 2 possibilities for the neutrino mass spectrum. You have here the normal ordering when this parameter is positive, or inverted ordering when it is negative. Currently, we have evidences for neutrino oscillations in experiments from atmospheric, solar reactor, and accelerator neutrinos. And each time of experiment is mostly sensitive to some part of this parameter space I've discussed before. So this is useful because we can just define kind of different sectors with enhanced sensitivity for each of the parameters. So for instance, in this slide, I summarize all the experimental data we have included in our analysis, and you can see these different sectors. We have the solar sector, where we have included all the solar neutrino experiments, as well as the reactor Camland experiment, that are mostly sensitive to the solar parameters, theta 12 and delta M21. We find as well the atmospheric sector, with results from Super Kamiokande and from Deep Core, also from Antares, where they are sensitive to the atmospheric parameters delta 2,3 and delta M31. We have also the reactor sector with Daya-Berren and Double Shaw, sensitive mostly to theta 1,3, and finally the accelerator sector with experiments Minos, T2K, and NOVA that are also sensitive to the atmospheric parameters. And we will see there is a sensitivity also to the delta CP phase that we will discuss later. So analyzing all this data together, we can perform a good determination of these neutrino oscillation parameters. So here you can find the table we have derived in our analysis with the best fit values for each of the parameters and also the 3 sigma range. And then you can see that if you calculate the relative 1 sigma uncertainty for all these parameters, we find that most of them are very well determined with uncertainties going just from 1% to 5%. On the other hand, we have the delta CP phase where the precision is not that good, especially in this analysis with the tension I will discuss later between T2K and NOVA. But we should keep in mind that just a couple of years ago, we didn't have any information at all on the CP phase. So having at present this sensitivity of the order of 17% is good enough. So the results of our analysis are also summarized here in these chi-square profiles for all the different parameters, for the 3 mixing angles on top, and for the mass splittings and the delta CP phase in the lower row. So here you can see that there are some parameters that are we can just increase the precision that we measure, for instance, the solar parameters or theta 1,3. But there are some other parameters that are not so much known as those. As for example, theta 2,3. As you can see now, the best fit prefers theta 2,3 above 45 degrees, so in the second octant, but still we have seen in the recent years that this could fluctuate with data, and probably this probably will change because there are new super K data I will discuss that now prefer first octant. So this thing is still not clear, not 100% clear. Then also about the sign of the delta M31 mass splitting I discussed before. Now current data prefer the sign being positive, corresponding here to the profile, to the blue profile, corresponding to normal ordering, because you can see this magenta line corresponds to inverted ordering, and there is a difference in chi-square of about 9 units. So now there is a 3 sigma preference for normal ordering, but also this thing is not definitive. This should be, we need more evidence on that in order to claim that we have measured the sign. And finally, also on the CP phase, there are some indications that the phase is maximal, especially for inverted ordering, here in the magenta line. But now in normal ordering, it is not that clear because, for instance, NOVA will prefer smaller values of delta CP, so still it is not clear what is the value of this delta CP phase. And I will focus on these more unknown parameters. Now let me go a bit sector by sector. For the solar sector, we know that solar experiments have measured the oscillations for more than 50 years, confirmed after Snow and Camland. And in our analysis, we include experiments using different techniques, radiochemical and also real-time experiments. And as observables, we include neutrino spectrum, day-night asymmetry. And in the solar sector, we also include the Camland data that are also sensitive to the same parameters. So analyzing all these results from the solar sector, so we get these allowed regions for the solar parameters. And then we can appreciate that there is a 2 sigma mismatch between the best fit value preferred by solar in black and Camland here in blue. But this is a long-standing mismatch, but probably this will change in the near future because in Neutrino 2020, there were new data published by the Super Kamiokande collaboration that now show that solar data prefer slightly larger value for delta M to 1. So the tension reduces from 2 sigma to 1.4 sigma. So going to the reactor sector, here the measurements are dominated by this new generation of short baseline reactor experiments, where we can find Daya-Bay, Double Shaw, and Reno with several cores and several detectors near and far. And also analyzing together all these results, we can determine the parameter, essentially theta 1,3 and also the atmospheric mass splitting. So here you can see the regions we can obtain from Valle and Reno with the pre-neutrino data. You can see that the precision is dominated by Valle. But Reno published new results with more statistics in the Neutrino 2020 conference, preferring a slightly larger value of the splitting and a slightly lower value of the angle. And then these are the preliminary results, but still you can see that the precision is dominated by Valle. So concerning the atmospheric sector, we include not only the atmospheric experiments, Super Kamiokande and Dallas and ICHEP, but also the accelerator long baseline experiments, MINOS, T2K, and NOVA, that were designed in order to confirm the atmospheric neutrino oscillations. So if we analyze these results, we find the allowed regions in the parameter space. In the top row, you have the regions from Super Kamiokande and deep core, and below you have the regions determined by the long baseline experiments. So I said before that one thing that it is not fully clear is what is the octane of theta 23. So in order to see the effect of each data sample on the octane of theta 23, we have prepared this plot where you can see the allowed region as long as we are including data in the feed. So you can see in black that the combination of long baseline experiments, T2K, MINOS, and NOVA, prefers theta 23 in the first octane. Here you can see with the black triangle in the plots. You have, as always, you have in the left plot normal ordering and right for inverted ordering. But once we combine long baseline with atmospheric data, we see that the preferred value of theta 23 shifts to the second octane. Here you have the square, the blue square. And finally, when we combine with reactors, we essentially fix the value of theta 13 measured by reactors, and then the best fit value stays in the second octane with this value. The science square of theta 23 is 0.566 for both orderings. What will happen? This is the picture we have so far, so preference in the first octane. But as I commented before, there were new Super Kamiokande data presented in the Neutrino 2020 conference that it seems that now Super K prefers theta 23 in the first octane. So we will have to see how this impacts the status of the octane once we will include this data in the global feed. So what about the CP phase? The CP phase, the situation is a bit different in normal ordering and inverted, because in normal ordering there is a tension between NOVA and T2K and Super K. Because you can see here NOVA prefers delta values close to 0, while T2K and Super K prefer maximal values of CP. So as a result, we have this determination here, and less sensitivity to the delta CP phase in normal ordering compared to inverted ordering, where all the experiments are in agreement about maximal CP phase. So this is the situation, the profile for the delta CP phase in normal ordering, inverted ordering, and there is, as I said, a worse sensitivity in normal ordering due to this tension. And in the future, it is expected to be even worse, because as published in the Neutrino 2020 conference, new T2K and NOVA data are even in more tension. So this for sure will disfavor the sensitivity in normal ordering. So finally, I would like to discuss the mass ordering. So we have seen, I have commented that there is a preference at the 3 sigma level of normal ordering over inverted, and this comes from the interplay of different data samples. Here you can see the detailed list, how we can go up to this 3 sigma, combining the different experiments. And at the end, we end up with a 3 sigma preference for normal ordering. And here you can find, I will not enter into details, but this sensitivity for normal mass ordering comes just for oscillations, but there are some other data that can help into our understanding of mass ordering. So for instance, here in the same paper, we have included information from tritium beta decay, neutrinos double beta decay in cosmology, in order to improve our sensitivity to the mass ordering. And we find that essentially, thanks to cosmology, we can improve a little bit the preference for normal ordering. So what will happen in the future? So in the future, and this is the sensitivity we have so far. So the data published in Neutrino 2020 show that Super K atmospheric analysis now has a weaker preference for normal ordering. Also in T2K, the measurement of theta 13 in T2K for inverted ordering is more in agreement with reactors. And there is a more intense T2K and nova tension that will worsen the status of normal ordering. And all these three items combined together will result in the fact that the preference for normal ordering will fall below 3 sigma. But in any case, we are working on that. This is a work in progress. Okay, and here's just the summary of the talk. I have discussed the current status of oscillation parameters, and I have commented also a little bit what we can expect from the new data published in Neutrino 2020. So I can just leave it for you to read because I'm over my time. Thomas?
Okay, thank you, Mariam. We have time for a short question.
So should I stop sharing my screen or?
Just
okay.
So there is one question in the, if double show is included in the reactor data for theta 1,3 on slide 12.
Yeah, not in this analysis. We have included up to the analysis in 2018, but not this time, because we have checked that the sensitivity, is not affecting much, including double show or not. So for this reason, this time we haven't included. The same applies to Antares.
Okay, time for one more quick question. Yes, please, Peter.
Hi, thanks. You mentioned that the significance for the mass ordering is delta chi-squared equals 9.1, and then stated that that's a 3 sigma result. Have you verified? Yes. Have you verified this via Monte Carlo? Because Wilks theorem, I don't think Wilks theorem applies for non-nested subsets.
So, sorry, could you please reply, Peter? I haven't heard the last part.
Yeah, sorry. You wrote. Have you verified that Wilks theorem is satisfied? Because in general, that's not true for the mass ordering.
Yeah, no, we just took it just from the delta chi square.
Okay, thanks.
Okay, good. So let's move on. If you stop sharing.
Yes,
now.
yes, done. Okay.
So we move to the next talk by Justin Evans about constraints on sterile neutrino.
Okay, let me make that full screen. Is that working now, Thomas?
Yes, looks good. Very good.
Brilliant. Okay, so I'm presenting a paper we released recently that makes direct comparisons of sterile neutrino constraints from cosmological data and some oscillation data. So the motivation for this comes from the well-known tension on sterile neutrinos. It's quite well illustrated by this plot that was recently released by the MINOS Plus and Diabay collaborations, where experiments like LSND and MINErva see high significance evidence for electron neutrino appearance from a muon neutrino source, and interpret that as existence of sterile neutrinos. And so LSND allows these green regions and MINErva this blue region over quite a broad range of mass splitting up to the new 4th mass state, delta m squared 4,1, and again over a fairly broad range of possible mixing angles, where this theta mu e is a mixing angle that governs the rate of this new mu to nu e appearance. But of course, the tension comes from the fact that a lot of other experiments, particularly those looking through disappearance channels rather than appearance channels, seem to have ruled out the possibility of a sterile neutrino explanation here, especially in the usual sort of 3+1 phenomenological model that's used to model or to quantify these observations. So here, a combination of muon neutrino disappearance data from MINOS and MINOS Plus with electron disappearance data from Diabay and Bouget exclude everything to the right of this red region, which includes most of the LSND MINErva region. But there's one other source of information on sterile neutrinos that's often not shown on these plots, and that's cosmology. Because the impact of an extra neutrino flavor, if that thermalizes in the early universe, will impact the shape of the cosmic microwave background, particularly the power spectrum of the CMB. And that's shown here. Here's the power spectrum. The dark blue is your sort of vanilla cosmological model. Red and blue are what you get if you add in an extra sterile neutrino flavor at a couple of different masses, and you can see it moves these wiggles around. And in cosmology, the parameters that you quantify this with are the effective sterile neutrino mass, which is sort of related to its thermal mass, and then this thing called delta N effective, which is the effective number of extra relativistic degrees of freedom you have in the early universe. So one additional flavor that's fully thermalized in the early universe will give a delta N effective of 1. But the question is how you relate the cosmological and oscillation data and how you interpret them together. And so we've had a look at that using a prescription actually set up by Hannestad et al. In this paper, and a piece of code they made available, which has the wonderful name of lasagna. And that allows a conversion between the mixing angle and the mass splitting, so that's the oscillation parameter space, into the delta N effective parameter of cosmology, and a similar prescription for getting into M effective sterile, the mass. And what you can see is that for big mixing angles and large mass splittings up here, you have a full relativistic degree of freedom where your neutrino is, sterile neutrino flavor is fully thermalized. And down here, if your mixing angle is small or your mass splitting is small, actually your sterile neutrino doesn't really thermalize and you don't get that extra degree of freedom, even if it's there. And that's basically because, you know, increased mixing angle increases the ability of the sterile neutrino to couple to thermalize, and increased mass increases the temperature at which the thermalization happens. And so what we've done is applied this to recent oscillation data as a sort of global fit. And so we've taken this prescription and starting with electron neutrino disappearance, so diabase, nu E bar disappearance, we can apply this prescription as a function of theta 1,4 and delta M squared 4,1 and convert that parameter space into delta N effective, going as you'd expect from no impact on cosmology up to a full extra degree of freedom. For nu E disappearance, you just need to use a 1+1 model. You only need one mixing angle just to let your electron flavor mix into your fourth mass state. But what you can already see here is that diabase is actually quite strong at the low mass splittings where there's less impact on cosmology. Delta N effective is small. So you can sort of already appreciate here that maybe diabase is going to be a little more powerful than the cosmological measurements. And so what you can do is put that together with the cosmological measurements that come from Planck. And so this is now the Planck space, delta N effective, M effective. This is the Planck 95% exclusion, and Planck when they include baryon acoustic oscillations in lensing. So they exclude everything to the top right of this. And you can see at higher effective masses, Planck is way stronger in its exclusion than diabase, but at the low masses, diabase actually has a rather stronger exclusion. We've also put on here the reactor anomaly allowed region, which you can see is quite strongly excluded in this model. You can also go the other way, so you can take your Planck exclusion in the delta N effective, M effective sterile space and use this prescription backwards to convert into oscillation space, so to convert to theta 1,4 and similarly convert to delta M squared, and plot this on the oscillation axes. So here you have your diabase exclusion. We put on the reactant anomaly allowed region again, and also here in darker red, the gallium anomaly, and in green, the neutrino 4 allowed region. And you can see that again, the same sort of picture. Planck in blue is excluding everything to the top right. So at the higher mass splittings, above the delta M squared about 10 to the -1, Planck is much stronger than oscillation exclusions, but at the lower mass splittings, diabase is actually what's giving you the stronger exclusion. So that's the electron neutrino disappearance. The real interest is whether we can actually express that in the parameter space of electron neutrino to muon neutrino appearance. And to go here, you've got this mixing angle theta mu E, which governs that appearance. The challenge is that that's actually a mixture of two mixing angles, and so you have to let your muon and electron flavor mix into the fourth mass state. So now you need to go to a full 3+1 model. That's rather complex because you have to solve the quantum kinetic equations of neutrinos in the early universe in 4 flavors. So you have to make simplifications to make that computationally possible. And so to do that, we use something called the mean momentum approximation, a prescription for which was in this 2012 paper, which basically means we take the momentum distributions of neutrinos in the early universe and assume they all have the mean momentum, just one momentum. And also you have to push down to fully cover this parameter space into a degenerate region where the sterile mass splitting delta m squared 4.1 is actually the same or of similar order to the atmospheric mass splitting delta m squared 3.1. And so that becomes a rather more computationally complex region to deal with. But making that mean momentum approximation and pushing down into the degenerate region, we can overcome these problems. Just to show you what the mean momentum approximation does in our electron disappearance model I showed you before, where we can solve it exactly. The Planck exclusion with baryon acoustic oscillations goes from this blue dashed line to the grey dashed line when you put in the mean momentum approximation. So it marginally weakens the apparent Planck exclusion by making this approximation. But you can put it all together and convert your oscillation space into delta n effective, m effective sterile in this 3+1 model. And this is theta mu e, the appearance angle. Again, bigger mixing angle, bigger mass splitting means a bigger delta n effective, bigger effect on the early universe. And so putting it all together, this is what you get. And so again, here's your mixing angle, mass splitting, and here's your allowed region from miniboon and LSND. And it's excluded by much by the Diabet region. But what you can see is the same sort of story, that Planck now is excluding everything above this blue line. And so even though Diabet does not exclude the top of the LSND allowed region, the Planck exclusion in this model is actually very strong up in these high mass splitting regions. And so this is a nice visualization of how the Planck exclusion actually impacts the oscillation parameter space. Just one little note is we published this paper before the most recent Diabet-Minos combination came out. So this contour here is actually the 2016 version of the Diabet-Minos-Bouguer exclusion region. So in conclusion, what I've shown is a paper that performs a comparison of the cosmological and particle physics searches for sterile neutrinos and compares those in the same parameter space. And what we see for electron neutrino disappearance is that the cosmological limits are stronger at higher mass splittings above the delta m squared 4.1 of 0.1 electron volts for electron neutrino disappearance, which corresponds to an M effective sterile of about 2 electron volts in the early universe. And Diabet is more constraining at lower masses. But of course, the thing always to note with these comparisons is that these cosmological limits are model dependent. You can of course start playing with the models of your early universe to find ways to stop your sterile neutrinos from thermalizing by adding in new interactions and things like that. And then a similar story for the muon to electron neutrino appearance. The cosmological limits, so cosmic microwave background, are stronger above a delta m squared 4.1 of 5 times 10 to the minus 2 electron volts squared. Whereas Diabet-Bouguer-Minos combination is stronger below that sort of mass splitting, and that again corresponds to a delta M effective of around 0.2 electron volts. And so to finish off, there's a link to the paper. Okay, thank you. Any questions?
Okay, thank you very much. We have time for some questions. Please raise your hand. I don't see a hand, so let me ask a quick question. So I understood that here you consider just a standard cosmological scenario. You know, there are some ideas to go to more exotic things like neutrino interactions and things like that. So can you comment on those ideas?
So basically all of these ideas revolve around, you know, the idea of trying to stop those sterile neutrinos from thermalizing in the early universe to limit their impact on the CMB. And so generally, you know, of the ones I know of, what that does is weaken the Planck exclusion in the oscillation space. It basically, you know, finds a way to bring the appearance results back into agreement with the CMB by just keeping that sterile neutrino out. So quantitatively, the one sort of new model we looked at actually in a previous paper was a lepton asymmetry. So introducing a lepton anti-lepton asymmetry in the early universe. You can actually quite strongly, you know, reduce the strength of the Planck region. I mean, I don't, you know, have the plot in here, but, you know, I seem to remember that, you know, the Planck exclusion, you can start pushing more sort of up to this sort of region. And so, yes, you can play quite a lot of games with these new exciting models to make these things compatible with each other. And I think, you know, so it's, you know, lepton anti-lepton asymmetry, new interactions for sterile neutrinos, and I think introducing reheating in the early universe is another good way of messing around with the thermalization as well. So those are the sort of three categories you tend to see.
Okay. Okay, good. I don't see any further hands up, so let's move to the next talk.
Okay.
It will be by José Valle about neutrino oscillations, flavor theories, and dark matter. And so we will play the video of the talk, right? Let's see if this works.
Hello, everyone. My task here is to briefly review the legacy of oscillations for particle physics. We have already heard a nice recap of the oscillation parameters, so I move directly to their implications for neutrino mixing. The first pattern to highlight here is the 3B maximum mixing, which, although from diabase and Rino, it still provides a useful starting point from where to generalize the mixing pattern so as to obtain realistic ones and predictive ones. As indicated here, this is the prediction of one of these patterns in the plane of the poorly determined oscillation parameters, the CP phase and the atmospheric, showing the prediction in green compared with the generic determination from global fits indicated in magenta. So one sees that they intersect within a very narrow range of delta CP, indicating high level of predictivity. I should stress that this is just one particular example. There is a whole class of patterns, generalized TBM patterns, which can be obtained systematically from the original one by exploiting symmetries. Bilarge lepton mixing is another interesting pattern which exploits the observation that the largest quark mixing, the Kabibu angle, is similar to the smallest lepton mixing, the reactor angle. So perhaps this small parameter may be used as the expansion parameter for the lepton mixing matrix so as to obtain predictions for the mixings from the fact that the reactor angle is well measured. You see here the solar and the atmospheric angle predictions. Again, this is just one example out of a class. Unitarity is an important task now that we reached the precision age. Moreover, seesaw-based schemes do expect deviations from unitarity, and even though these deviations, their magnitude is not fixed, their general structure is, and all you have to do to describe non-unitarity in a complete and rigorous way, you just pre-multiply U by a triangular matrix in which the diagonals are real and close to unity, and the off diagonals are small but complex. Nothing is known about the phase of these three, so all in all, we have just constraints on the 6 moduli shown here, and it is fortunate that the short distance physics program at Fermilab is ideally suited to improve upon these alphas. And this is not only interesting as a seesaw probe, but also a necessary step towards having a robust long-term CP determination program at the far detector. So much for oscillations. Double beta decay is the next point. The neutrinoless variety can be induced through the exchange of massive neutrinos. This is the standard mass mechanism. And it has 2 branches, for normal ordering and for inverted ordering. Normal is currently preferred by oscillation at 3 sigma. In this parameter space, we have already 2 bands that are excluded. The brown is from Kamlan-Zen, and the vertical band is excluded by cosmological CMB and baryon acoustic oscillation data from this recent paper. So neutrinos cannot be nearly degenerate. The next best bet is that one of them is massless. The first term drops. There can be no cancellation between the other two. So you are guaranteed that the amplitude is non-zero, although it will lie within the experimental sensitivity of the next generation experiments only if the ordering is inverted. However, in this case, the situation is promising much more than the generic one for 2 reasons. First, the lower bound lies higher than the generic one up there. Second, the width of the region is much smaller than the generic one up there. So one may entertain the hope of actually determining the magnitude of the Majorana phase for the first time. Finally, if all 3 neutrinos are massive, there are no guarantees for a lower bound on double beta, but in the presence of family symmetries, it often happens that these lower bounds exist, even for normal ordering. So on this positive note, I turn to theory to state first that the seesaw provide a popular paradigm for neutrino mass generation, to a large extent because of the fact that it gives a dynamical way in terms of which one can understand the small neutrino mass by minimizing an extended Higgs potential with extra expectation value coupled to neutrinos. In fact, these extended neutrino Higgs sectors may actually hold the key to the stability of the electroweak vacuum, which is a very interesting and potentially profound implication. But I will turn back again to the diagrams involved in the mediating small neutrino masses a la seesaw. For type 1, you exchange heavy right neutrino. For type 2, you exchange heavy scalar triplets. The original seesaw papers, most of them were inspired by a Sautin or left-right symmetry, except ours, 40-year-old paper. We were inspired just by the standard model. By being less ambitious, we were more general in the sense that we could allow for any number of right-handed neutrinos without necessarily matching the number of left neutrinos. So still today, one can have such theories with, for example, only 2 right-handed neutrinos and 3 left-handed neutrinos. This leads to 1 massless neutrino, a missing partner seesaw, and hence a bound on M beta beta, lower bound on M beta beta. Conversely, one can have more rights than lefts, and these theories actually contain the template theory for low-scale sensorialization, in which neutrino masses arise from the exchange of a mediator that can also be produced at collider experiments. And moreover, concerning the propagation of light neutrinos, the deviation from unitarity can be sizable. Seesawing is not a privilege of Majorana neutrinos. It may also take place for Dirac. This is type 1 Dirac. This is type 2 Dirac, and so is this. There is a whole bunch of papers, recent papers on this, which I cannot go through. I will jump immediately to the flavor problem. In my opinion, the deepest challenge of particle physics, and one for which the oscillation experiments have also provided an important input by establishing the pattern of lepton mixing to be completely at odds with the pattern involved in the CKM quark mixing matrix. In fact, in trying to explain these from first grounds, one obtains within a very broad class of theories a simple relation that is shared amongst all of them, namely this quark-lepton mass relation, which I call golden. This brings me to fundamental theories of flavor. My first comment is that extra space-time dimensions do provide the ideal setting for formulating fundamental theories of flavor. I'll give two recent examples. An example from 6 dimensions, compactified on an orbifold, in which one has no choice as to what is the 4-dimensional family symmetry. It must be A4. And this happens to be the simplest we can use to stack the 3 families in a triplet. And it leads to this golden quark-lepton mass relation. Moreover, it predicts leptonic CP violation. Both the Majorana phases are predicted, and this translates into a M beta beta prediction, shown here in dark, but also it predicts, again indicated in dark in the middle panel, the value of the Dirac phase of neutrino oscillations. But more importantly than the value, it is the first fundamental theory of flavor I know of in which the sign of CP violation is also predicted. If you have extra dimensions, you might as well contemplate the possibility that at least one of them is warped. We know how to handle this, just Einstein's equations. And the first positive observation is that this program is completely consistent with the imposition of a family symmetry, capable of giving predictions for the oscillation parameters as well as for double beta decay. Moreover, because of this geometrical warped nature, this extra warped space-time dimension opened hopes for an ultimate dream theory in which all hierarchies in particle physics could be explained just by geometry. To sum up, just one comment on the dark matter candidate. In a nutshell, the dark matter candidate could just be a weakly interacting massive particle that we have heard a lot for the past at least 30 years. However, the WIMP that appears here is not necessarily bears any relation with supersymmetry. Rather, it is intimately related with the mechanism of generating neutrino mass. Indeed, it mediates radiative neutrino mass generation. This original idea dates back to Ernest Ma, but has now been converted into a very promising paradigm for modeling dark matter and for modeling neutrino masses. With this, this brings me to my summary slide, and I take the opportunity to thank the organizers for their kind invitation and the audience for the attention.
Okay, thank you for the talk. So we have time for a quick question, please. Yes, there is a question here. I read the question. What is m⁴ symmetry and how can it be softly broken?
Sorry, I could not listen to the question.
What is m⁴ symmetry
m⁴.
and how it can be softly broken?
I do not locate the question in the context of the talk.
Okay.
I talked about A4 symmetry, and I did not use soft breaking, by the way.
Okay, maybe there is some misunderstanding. I propose that you use the chat tool to sort this out. So maybe if you can pose your question in the chat and then you can try to sort it out there. Okay. Any further question? No, this seems not to be the case. So thanks again. Move to the next talk. Next talk will be by Arie Bodek about extraction of the optical potential for final state nucleons and delta resonance for electron and neutrino scattering on nuclear targets. Please.
Can I go ahead and share?
Yes.
Can I share? Do you see my screen? Hi, can you see my screen?
Yes, we see the screen.
Okay, fine, so I can start. Okay, my talk mainly refers to the determination of neutrino energies in neutrino oscillation experiment, in which you need to model quasi-like interaction like quasi-elastic and delta resonances. I refer to two papers. One was published last year and one was just recently published a week ago. And this will give additional details. So the modeling neutrino energies in quasi-elastic and like events, especially in detectors such as T2K and super K, where you only measure the final state lepton, requires good modeling of the removal energy in the initial state Brown nucleon, which you don't observe, and then the Coulomb potential for charged particles in the final state. And then, as I will discuss, the average of the real part of the nuclear optical potential for quasi-elastic and delta resonances. Now, the value of the removal energy are extracted from E prime P spectral function in our first paper. VEF and UQE, which is the optical potential for quasi-elastic and delta resonance, are extracted as a function of final state baryon kinetic energy from the peak positions of the inclusive electron scattering data on nuclear target. And we compare this optical potential for quasi-elastic scattering to calculation by Kubik et al. We also find that the optical potential for delta is more negative than the optical potential for the quasi-elastic, but about 1.5 times as large. It's negative. And we present results for other nuclei. And this is different from GWU, which assumes that the optical potential for the delta is 2/3 the optical potential for quasi-elastic scattering. All right, so the way the optical potential enters is the fact that when we scatter in impulse approximation from a bound nucleon, there's the removal energy on the left-hand side, and then the final state energy is just the kinetic energy of the final state proton plus its mass. However, it's produced in a potential. It's produced in a nuclear potential, and it's produced in a Coulomb potential, and one has to account for those potentials in an energy conservation equation. Similarly, the electron, for electron scattering, when you extract compared to electron scattering to neutrino scattering, you have to account for the fact that in electron scattering, you have the acceleration of the initial state by the Coulomb potential and the deceleration of the final state by the Coulomb potential as well, which changes the value of the form momentum transfer. Okay, so the nuclear optical potential has both a real and imaginary part. The imaginary part is sometimes referred to as the final state interactions in Monte Carlo generators, and this basically results in inelastic scattering of nucleons on a nucleus in a final state, say by emission of pions or scattering with final state with spectator nucleons. But here we only discuss the real part, which depends on density, radius, and kinetic energy of the proton in the final state. Now, the optical potential, you can talk about the initial state optical potential, which is just the binding potential, and the final state optical potential. But those potentials are dependent on the kinetic energy of the particle. Now, we are not going to use the optical potential in the initial state because we can measure its effect by measuring the removal energy from E'P experiments. So that's a parameter that we measure. We don't have to assume, but we need to determine the final state optical potential by looking at a shift of the position of the quasi-elastic peak with respect to the cases where the optical potential is equal to zero. And it does affect the energy of the final state lepton. So first, accounting for Coulomb energies, the Q square, so we're going to use electron scattering to extract all of our parameters, electron scattering data. So for the electron scattering data, because of the 1 over the Q to the 4th scattering and the dependence on Q square, you have to account for the Coulomb potential both in initial for initial state electrons and final state electrons, as well as the final state protons in quasi-elastic scattering. And we do that in analysis by the expression given on the top of this page. All right, so basically the analysis is relatively simple. On the right-hand side, you see, say, quasi-elastic scattering, electron scattering, the Q square equal to about 0.13. And you look at the impulse approximation Fermi gas model, and you put in the binding energy, removal energy effect, but you account for no optical potential at all. And what you see is that the dashed red line, which shows you that the position of the quasi-elastic peak as you expect from just the binding energy or removal energy effect. And you see that it's shifted with respect to what you see. So the way you correct for it is because the final state proton is produced in a nuclear potential. The energy conservation equation should include both kinetic energy and potential energy. And on the left-hand side, you see the expression of the energy conservation, and you said the initial state has the removal energy, epsilon, and the final state has both the optical potential and the Coulomb potential. And you do a similar analysis for the delta resonances. So let's go to the next slide. I've just added on the bottom here the case for the delta. For the delta, we should be more careful at modeling the quasi-elastic scattering because of 2p2h, and so we describe it with the effective spectral function, and then now we looked at the Fermi gas model smearing the electron scattering cross sections on free protons and free neutrons, and seeing what happens. And what you see again is if you don't account for the optical potential, you have the dashed red curve. So you have, and it's shifted. So you have to account for the optical potential in the final state to get it in the right place. Okay, so now let's compare to theoretical calculations. There are calculations which look at the optical potential and extracted from proton-nucleus scattering data. And one of the examples is the parameterization of Cooper, Hammer, Clark, and There were two different papers, 1993 and 2009. Now, the Jibu calculator also uses a similar approach, and you can see the comparison on the right-hand side between the optical potential set R equal to 0 as a function of the kinetic energy of the final state nucleon for the Cooper 1993 and Jibu model, and they are relatively similar. Now, the electron and neutrino interactions occur at any location in the nucleus. So the one parameter that you want to get is the average optical potential over the entire nucleus that occurs when you kick out a nucleon or a delta that you produce. So here's the results for both quasi-elastic scattering and delta. The quasi-elastic scattering optical potential is in black little dots. And you see that it's somewhat less than the theoretical calculations for Cooper et al. And now the optical potential expression for the delta is the red and blue points in their different colors, depending on which data set you use. And you see that's more negative than the quasi-elastic scattering. So now let's talk about the effect of the determination on neutrino energy, neutrino oscillation experiment of this analysis. So a simple way to combine all the various effects into so-called binding interaction energy, which is that if you use the offshore formalism, you can just write down neutrino plus mass minus the interaction energy, which includes all the effects, is equal to the final state kinetic energy plus m square, square root. So now the interaction energy can be defined as the removal energy, and then the optical potential and the Coulomb potential, all in one number. So you see the inclusion of the optical potential is effectively, actually, since it's negative, it sort of reduces the removal energy. So for the electron scattering on a bound nucleon, let's say in carbon-12, our result indicates that the interaction energies for the range of final state baryon kinetic energy from 0.05 to 0.3 GeV vary from 5 to 28 MeV for the nucleon and from 11 to 29 MeV for the delta. So you can't use a fixed number for this interaction energy. It has been done in neutrino Monte Carlo generated. You have to use a number which depends on the kinetic energy of the final state nucleon, because the optical potentials are depending on the kinetic energy. And you can see that unless you account for it properly, you can get as much as an uncertainty of about 20 MeV in your determination of the neutrino energy in neutrino oscillation experiments. Now, the formalism of Moniz et al. Uses what we call the on-shell formalism. The on-shell formalism, the energy conservation expression includes the kinetic energy of the initial state nucleon in the expressions, and because it does, then in the on-shell formalism, which is say in the Monte Carlo of Newt, while the offset formalism is in the Monte Carlo of Gini, but the on-shell formalism in Newt and Moniz defines energy conservation this way, and therefore the interaction energy includes the average kinetic energy of the initial state nucleon. And here again, if you use all the parameters that we measure, then the interaction energy varies from 21 to 44 MeV for the nucleon, and from 4 to 44 MeV for the delta. So again, it's a big effect if you don't do it properly on the measurement or estimate of the neutrino energy in neutrino oscillation experiments. So, discussion of delta resonance. We find that the optical potential for the delta resonance is about 1.5 times as large as the optical potential for the quasi-elastic. And Jibu uses 2/3 instead of the optical potential of the nucleon. So we are sort of opposite direction. Now, naively, I would think that the delta lifetime is about 5 times 10 to the 24 seconds. So for all values of energy transfer in this particular analysis, the delta decays inside the nucleus. So consequently, I would expect that the optical potential for the delta should be somehow related to the sum of the optical potential of the nucleon and the optical potential for the pion in the final state, since both of them are produced in a nuclear potential. And therefore, I would think that our result, which is that it's 1.5 times as large, is sort of, I would reasonably expect. So then there are different kinds of fits in there. There was an extraction of the potential in 1990 by O'Connell and Selak, but their spectra had a large contribution from various backgrounds because they look at very relatively high Q-square data. And here we compare our result to theirs. Our result for the optical potential of the quasi-elastic is similar to theirs, but the optical potential for the delta, they have a dashed red line, which is even more negative than ours, but we think that ours is more correct. So this is a summary of the results in one plot, which I already discussed. And then I will go to the conclusions of my talk, the following. Conclusions, we have extracted the removal energy for epsilon for various nuclei from E prime data that's published. We also extracted the optical potential of the nucleon and delta. And because the final state lepton and hadron energies in electron and neutrino scattering depend both on all those three variables, the fact that we've determined all those three variables reduce the uncertainty in the determination of the neutrino energy in neutrino oscillation experiments from 20 MeV down to, say, 5 or 8 MeV. And I think I ran out of time.
Okay, thank you very much. We have time for a very short, quick question. Please raise your hand if you want to ask a question. Okay, I don't see a hand, so I thank the speaker again, and let's move to the next talk. Next talk will be by Alexandra Parada Valencia on constraints on non-standard interactions, the neutron radius from coherent elastic Neutrino-Nucleus scattering.
Thank you. Can you see my slides?
Yes, looks good.
Okay.
Please.
Thank you very much. My name is Alexander Parada. I'm going to talk about constraints on non-standard interactions and the Newton radius from coherent elastic Neutrino-Nucleus scattering experiments. This work was developed with my colleagues Blanca Cañas, Estela Garcés, Omar Miranda, and Gonzalo Sanchez. Well, first, we have a brief introduction. Next, I will talk about sevens and non-standard interactions. Then, sevens experiments with the spallation neutron source. And finally, the conclusion. Sevens is produced when a neutrino interacts with a nucleus via a Z boson. The cross-section of sevens is 2 orders of magnitude larger than the other processes, as you can see in this figure. The coherent conditions is satisfied by these relations. Probably we will see more information about that in this talk later. On the other hand, the existence of sevens was proposed in 1974 by Daniel Friedman, and the observation of sevens for the first time was reported by the Coherent Collaboration in 2017. And in this year, 2020, was reported the detection of sevens on argon by Coherent experiment. Sevens opened the door to study many topics in the standard model and beyond standard model. For example, non-standard interactions, searches for sterile neutrinos, measurements on weak mixing angle, nuclear density distributions, among others. So in this direction, the main idea of this work is to study the future sensitivity of sevens experiments to obtain limits on NSI and nuclear parameters. Here we see the cross-section of sevens in the standard model. We can notice that this cross-section depends, for example, on the nuclear form factors, the nuclear recoil energy, the nuclear mass, and neutrino energy, etc. Here, the nuclear current vector couplings are given by these expressions according to the particle data group. So in a first scenario, we consider the NSI in future reactor experimental proposal of sevens. So in this case, the cross-section depends, as you can see here, depends on the NSI parameters and nuclear form factors. However, neutrinos from reactor experiments have very low energy. So in this case, we can approximate the nuclear form factor to 1. On the other hand, the theoretical number of events is given by this equation, where lambda corresponds to the antineutrino energy spectrum, and which is given by a polynomial of degree 6, as you can see in this expression. So in order to obtain limits from future reactor experiments, limits on NSI parameters, we made a chi-square analysis, as you can see in these expressions, where NSM correspond to the number of events expected by the experiment in the standard model, and NPAs correspond to the theoretical number of events. We also include here possible statistical and systematic errors throughout these terms. On the other hand, there are several experimental proposals that are trying to measure sevens from neutrino. So here we focus on two main experiments, CONI and CONUS. These experiments have complementary characteristics and are given in this table. So here we show the future sensitivity to non-universal NSI parameters. In this case, we have included only one parameter at the same time. As we know, it's difficult to predict the systematic error. However, in this case, we consider a systematic error of 2 and 8% being conservative. In this case, the magenta band correspond to the full 4% of systematic error, and the green bands correspond to the 8% of systematic error. In a similar way, we obtain the future sensitivity to flavor changing NSI parameters. We also include one channel here, the Itau channel, taking into account that other channels have been considered by other works. However, according to this result, we can say that in a future, this result would improve current limits obtaining from other experiments, as we could see in these references. Well, in order to obtain a more robust constraints, we also made a combined analysis from future CONI plus CONUS data. So in this case, we include the systematic error from reactor antineutrino flux, and we also included the correlations. So in these figures, we show the results for NSI parameters. For example, the blue bands correspond to the analysis with correlations, and the dashed line correspond to the analysis considering 2% of systematic error. we can notice that these regions are similar, qualitative similar. So we also studied the 7 experiments with the spallation Newton source in another scenario. So in this case, we focus on coherent experiments. As we know, the neutrinos are produced in this spallation neutron source when a high energy protons collide with a mercury target. So this collision produces pions and muons, and this particle decays, producing neutrinos. Maybe we will see more information in this talk later. In this case, the total neutrino flux is given by a sum of 3 terms, as you can see in this equation. So, as we mentioned above, the cross section depends on NSI parameters, but also depends on the nuclear form factors. In contrast to neutrino from reactor experiments, in this case, neutrino from spallation neutron source reach energies of the order of 52 MeVs. So in this case, the nuclear form factor is different from 1. Then we use the symmetricized Fermi form factor in order to express the nuclear distribution. As you can see, the Newton radius is related to the parameters CA throughout this expression. So we also made a statistical analysis from scission iodine coherent data. In this case, the theoretical number of events is given by this equation, where acceptance functions according to the coherent experiment is this, and the expression for the chi-square analysis is given by this expression, where alpha and beta correspond to the systematic errors of the signal and backgrounds respectively. So we minimize the function respect to the NSI parameter and nuclear radius. So in this figure, we show maybe the main, or one of the main results of the work for the allow region from scission iodide coherent data. In this case, we consider a constant quenching factor. So the blue region corresponds to the analysis from scission iodine, and the red region corresponds to the combination, the scission of this scission iodine with future CONUS data. So we can see that we obtain more restrictive, we will obtain more restrictive constraints in this case. Well, here we also show the lower region, but this time from argon coherent data. So in order to present maybe the most current measurements of coherent experiment. To complete these results, here we show the results, but this time considering the future proposal of coherent experiment to measure sodium iodine, to measure 7 on sodium iodine coherent data. So in this case, the detector feature was taken were taken from these references, and the acceptance function was considered equal to 1. And in the case of Coney experiment, we consider a 30% of deviation from the standard model. It means that the that the CONI experiment measures an excess of events or deficit, maybe we could see new physics in these parameters, NS size or nuclear radius. Well, so to end this talk, we have the conclusions. The future detection of sevens in reactor anti-neutrino experiments and new measurements in these processes, including neutrinos from spallation neutron source, could give rise to precise estimation of the neutron radius and NSI interactions. Moreover, sevens combined analysis from nuclear reactors and spallation neutron source leads to better constraints on the neutron radius and NSI parameters. We have to highlight here that we obtain complementary information from these two kinds of experiments. Thank you very much.
Thank you for the talk. Are there questions? Please raise the hand. Okay, I see a question here in the chat. How do you consider the reactor anomaly in your study?
Okay. In this study, have not considered the reactor anomaly. So maybe we consider a possible excess of the events, but not exactly related with the reactor anomaly.
Okay, I see no further questions, so let's move to the next talk. Thank you again.
Okay, thank you very much.
So the next talk will be by Salvador Rosauro-Alcaraz about neutrino portals to dark matter. Very good.
Can you see the screen?
Yes, we see the screen.
Great. So let me start by thanking the opportunity to talk here. Today I'm going to talk about some work I did with my collaborators on neutrino portals to dark matter. So as you know, there is dark matter in the universe, and we know this thanks to various different probes, cosmological probes and gravitational ones at very different scales, from the rotation curves of galaxies to the study of the power spectrum of the CMB. Now, thanks to this, we know the relic density to be about 0.12, and we can now think of a mechanism to produce dark matter in the early universe. One of the simplest ways to do this is through the thermal freeze-out mechanism, in which, as the universe expands, dark matter stops interacting fast enough such that its relic density freezes out. The good thing about this mechanism is that it relates the production mechanism through thermal freeze-out with the indirect detection and direct detection searches. So now we can go to our experiments at Earth and look for a signal. And it turns out that so far in direct detection experiments, we don't have a definite signal for a dark matter interaction with standard model particles. There is the recent Xianguo 1-ton result on electron recoils, but it's still not definite. And we can also go to indirect detection searches. And again, we have some hints from the galactic center on some excess, but looking at dwarf spheroidal galaxies, we don't observe such a signal. So again, we don't have a positive signal of dark matter. So the possibility we're going to study here is that the dark matter is actually interacting primarily with neutrinos, which turn out to be the weakest interacting particles in the standard model. And if that is the case, then we will be looking for the annihilation of dark matter in the Milky Way halo or the galactic center, producing a monochromatic flux of neutrinos that will arrive to Earth, and we will detect them in Super Kamiokande, for example. And here you have this reference with a list of all the possible constraints from different experiments on dark matter annihilating to neutrinos. Now, the simplest thing we can do, or we can think about, is to couple dark matter directly to the standard model neutrinos. Now, the issue with this is that in the standard model, neutrinos belong to an SU2 doublet, and therefore, if we comply to gauge invariance, we can, in the effective field theory language, we can, for example, write this kind of operators, where we are directly coupling dark matter to charged leptons as strongly as to neutrinos. So when we go and study the production and constraints, we, for example, coupling dark matter to the electron doublet, we see that although we can produce the correct relic density along the blue line here, Planck data on the energy injection of the CMB through dark matter annihilations to electrons actually constrains and rules out most of the parameter space. Now, if you only couple dark matter to the tau doublet, then of course, whenever the dark matter mass is lighter than the tau mass, the only possible channel to annihilate to is two neutrinos. And in that case, we indeed observe that the parameter space is fully constrained only by neutrino experiments. Now, however, in this case, we would need to have some mechanism to explain why dark matter is only coupling to the tau doublet instead of to the three generations more generically. And this is where we remember that the neutrinos are actually massive particles, as we know from neutrino oscillation experiments, and that we need to explain the origin of their mass. One of the most popular ways to explain their masses is through the type 1 seesaw mechanism, in which we introduce singlet red-handed neutrinos, which can have a large Majorana mass, explaining therefore the smallness of neutrino masses, and where the mixing between active and heavy states is given by the ratio between the Dirac and the Majorana mass. Now, one phenomenological problem with this model is that even for order 1 Yukawas, you have the Majorana mass at the GAT scale, and therefore the mixing is really small. So there is little hope to have any experimental signatures of these kind of models. Another possibility is to work in the context of low-scale seesaws, where we assume that there is an approximate lepton number conservation preventing and protecting neutrino masses. Here we will see the example of the inverse seesaw, where we introduce Dirac singlet neutrinos, which have a Dirac mass and which can then have a small Majorana mass, this mu sub L here. Now, light neutrino masses in this case turn out to be proportional to the small lepton breaking scale, while the mixing between heavy active and heavy states, can still be sizable. In fact, in the lepton conserving case, although we have massless neutrinos, you can still have order 1 mixing. So for the phenomenology we're interested in here with the dark matter, it is enough to consider 1 Dirac singlet neutrino, which turn out to have and forget about the Majorana mass. So we can consider light neutrinos to be massless, and the heavy neutrino will have the following mass with the following mixing. The relation between flavor and mass eigenstates will be given by this unitary rotation U, which is basically proportional to the mixing parameter. So what we're going to try to do here is to couple dark matter to the singlet neutrinos in the context of low-scale seesaws. Now, through large mixing, we will eventually get a coupling after spontaneous symmetry breaking between the active neutrinos and the dark matter. And we study this with 2 possible mediators. The first one is with a scalar mediator, and the second with a vector mediator. Now, for the scalar mediator, we introduce the Dirac dark matter and the scalar, and we couple it to the left-handed part of the singlet Dirac neutrino. Now, the scalar and the dark matter can share the same charge under the U1 dark symmetry, and it is, in this case, it is possible for the scalar to be the dark matter if it's lighter than the Dirac Dirac fermion chi, but the cross-section turns out to be velocity suppressed. So here we'll be interested in the case in which dark matter is the dark matter is the Dirac fermion, because the signal at the experiment is larger. Now, after spontaneous symmetry breaking, you see that we get a coupling between the dark matter and all the mass eigenstates for the neutrinos. So we get a coupling between dark matter and light neutrinos. And the annihilation cross-section to these light neutrinos is proportional to the fourth power of the mixing. So you see here why it was important from the beginning to have to work in the framework of low-scale scissors with large mixing. Given that the direct detection constraints from the interaction of the dark matter to quarks are very strong, primarily from Xianguo, we need to consider the possible annihilation to charged leptons and quarks at the loop level. And we've done so by computing these loops and introducing these effective operators, which could in principle constrain the parameter space. Here we have some results for in the parameter space of the dark matter mass and the scalar mass for two different couplings between the dark matter and the singlet neutrinos. A coupling of order 1 and a coupling at the perturbativity limit. In the left panel, we can see how along the blue line, well, in both panels along the blue line, we reproduce the relic density, and the pink band here in the left is basically a bound on the dark matter mass to avoid the messing with the N effective in the early universe. Now the mixing here is to the tau neutrinos, because it's the less constrained one, and therefore it will dominate the phenomenology. But in principle, you can have a mixing to the three families, and you can see how the allowed parameter space is only constrained here by neutrino experiments. This bound here is primarily coming from super K, and that future experiments such as Dune or Hyper K can probe further in the parameter space and maybe eventually even get to the relic density target. In the case of a much larger coupling at the perturbativity limit, we see how, as expected, the bounds from Xianguo are actually important, and they constrain dark matter masses above about 10 GeV. But in general, the parameter space is primarily constrained by neutrino experiments. Now, for the vector mediator, we introduce a gauge boson, which could be the mediator of a new U1 symmetry, gauge symmetry, and we couple it to the left-handed part of the Dirac neutrino and the right-handed part of the dark matter in order to cancel anomalies. Additionally, we need to impose a Z2 symmetry between the dark matter and the singlet neutrinos to avoid their mixing and keep dark matter stable. Again, the annihilation cross-section to light neutrinos is proportional to the fourth power of the mixing. And in this case, we see that the cross-section, as it goes through an S channel, presents a resonance. Okay. Once again, we take into account the bounds from Xianguo and so on, from the annihilation to charged leptons and quarks at the loop level, and we present here the results. We observe how now the relic density line, where we reproduce the relic density, presents this resonance from the S channel, and that indeed the neutrino experiments are primarily constraining the parameter space. Once again, Xianguo constrains large dark matter masses for couplings at the perturbativity limit, but it's mostly neutrino experiments and future neutrino experiments which can help us probe these kind of scenarios. So this brings me to my conclusions. We still lack for a definite signal of dark matter standard model interactions other than the gravitational ones. So it is interesting to consider the possibility that dark matter is interacting with the weakest interacting particles we know in the standard model, which are neutrinos. Now, is this directly enough to avoid all direct and indirect searches? Well, if you couple directly to the lepton doublet, basically Planck and Fermi-Lat constrain most of the parameter space, unless of course the dark matter mass is smaller than the given charged lepton mass, so as the annihilation is only possible to neutrinos. And then of course neutrino experiments would be probed in that region of parameter space. A more interesting possibility would be these neutrino portals, in which you work in the framework of low-scale CISOs, which can have large mixing, and therefore couple dark matter to the singlet neutrinos, allowing you to explain the relic abundance and actually avoiding the bounds, or at least the interactions at tree level. If this is the case, then of course neutrino experiments are our only hope to find the dark matter. That's it. Thank you.
Okay, thank you very much for the talk. Do we have questions? Any comments? Yes, I see a hand up. Yes, please. I think you should be able to speak now.
Yeah, I think I'm unmuted. Thanks. This is Ben Kilminster from University of Zurich. So I had a question. So for the dark matter bounds on this, so for instance, the Darwin curves, is it the detector mass that's driving this, or the energy threshold, or the background rate? I mean, what I'm wondering is how other dark matter detection experiments would appear on this.
Yeah, I think actually this, just to point you to the reference, I think it is the detector mass, because they consider there, it's this one here. They consider there the bounds are coming just from coherent scattering, and I think the main difference is the mass you have.
Okay, I see. So this really would be the best curve on this plot then, because it would be the heaviest detector.
Mm-hmm. Indeed. Yeah.
Okay, thanks.
There is another question. Yes, please. Quick question. I think you can talk now.
Hi, can you hear me?
Yes.
Yes. Okay. So I have a curiosity. So is there any particular reason why are you sticking to inverse FIFA framework for low scale?
Oh.
I mean, you can also have radiative neutrino mass models like photogenic, where you have.
Yes, I mean, any kind of CISO in which you have large mixing, I mean, that it's not correlated to the light neutrino masses would work. I mean, we're actually not considering here light neutrino masses, so you can work in this was just an example.
Okay. Thanks.
Okay, very good. So thank you again.
Thanks.
And we move to the next talk. Next talk will be by Peter Denton about astrophysical visible neutrino decay.
Sorry. Can you see my screen?
Yes.
Okay, good. Sorry. Thank you, Tomas, for hosting this session. And this is my third ICHEP, and I really like the virtual format. So this is based on work I've done with Irina first a couple years ago, and then really mostly based on work I did with Oscillations that we finished up a few months ago. And the code and the data files are online. All right. So first I'm going to overview the global neutrino decay picture to put things in context, and then I'm going to talk about how we do the calculations, although I'll gloss over most of that for the short talk. And then I'll discuss the impact of the different parameters that go into this, and finally I'm going to show some suggestive hints of neutrino decay at IceCube. So in the standard model, neutrinos do decay because they have a mass, but it's loop suppressed and the lifetime is really, really long. We're never going to see it. But we should still test it anyway. So we could imagine throwing in some new physics that might induce this on faster timescales. So this is what that might look like. So the phenomenology can be classified into a couple of different, generic cases. The simplest one is invisible decay, where the decay products are sterile, or maybe they're too low of energy below your detector threshold, and this results in a depletion of the flux below the relevant energy. The more interesting one is visible decay. This is where the decay products are regenerated at lower energies, and then you can see this, and this induces a lot of very interesting phenomenology. So this is sort of the overall picture, sort of in a very casual sense. The lifetime tau over m is the characteristic parameter here. And we can see this spans many orders of magnitude. So these dash regions are things we don't have yet, but we might have. The cosmic neutrino background, of course, we're all waiting for when we might get out there. The DSNB is maybe not too far away with gadolinium loading at super K. The CMB provides very strong constraints. And then there are strong constraints from 1987A and then IceCube over there. So the IceCube region is around here. So the CMB seems to rule this out, and as does 1987A or any other future galactic supernova. But the difference with IceCube is that the IceCube situation is a little bit different, and I'll talk about that in a moment. So as I said, the DSNB and the CNUB are some ways away. The galactic supernova could come tomorrow or in a long time, who knows? And also for 1987A, even though we have some data, it's only a handful of events. And if nu1 is stable, and if the mass ordering is normal, although I had to update these slides due to neutrino, then the effect on the galactic supernova can actually be fairly modest. So that constraint isn't necessarily too strong unless all three flavors are decaying with similar parameters. What's great about IceCube is that it measures neutrinos with high enough energies that you can see all three flavors separately. Okay, not always very well, but you can see them, and over a fairly broad energy range. The downside is there's astrophysical uncertainties, but it turns out that they're actually not that big of a problem. All right, so how do you actually calculate visible neutrino decay? So first you have the standard model oscillations. This is the oscillation averaged or decohered regime. Then you include the depletion component where you deplete neutrinos below a certain energy. This is the invisible decay scenario, and then you include the regeneration component. This takes us to visible decay. And that last step, that's the tricky one. And so for that, you have to integrate over the decay location. You have to integrate over the initial spectrum, since there's this regeneration effect. You have to include multiple decays. That is, to go from nu3 to nu1, you can either go through the G3-1 coupling, which I'll show that in a minute, or you can go from 3 to 2 and then from 2 to 1. You also have to include cosmology because the expansion of the universe is relevant for IceCube, and then throw it all into the pot, see what comes out. There's been some previous work on this by many people. I've shown a few references here, and some of them do individual parts of this, like the cosmology part, but not the regeneration part, or some of them do the regeneration part, but not the cosmology part. So we do the full thing. So I'm not going to show the equations because it's a bunch of big integrals and a bit messy, but the plots I think are fairly instructive. So what I'm plotting here is some probability-like quantity for a given channel, nu mu to nu e. And this basically shows how the spectrum, whatever the initial spectrum is modified. So in the standard model in blue, there's no correction. And then depending on which couplings are turned on, you'll see depletion below some energy. And the shaded blue region is roughly IceCube's region of interest. And so you can see that, if you see some hardening of the spectrum, so what would happen here is you'd have some spectrum here, and then it would get harder, and then it would return to its initial thing, then that might be an indication of invisible neutrino decay. Now, when you include the regeneration component, you get a bunch of fun features here, and I think this is why this plot shows why this is such a fun phenomenology. Depending on which couplings are on, you can have scenarios like the green one where it's entirely larger than the standard model case, or the orange one where it's entirely smaller than the standard model case. Or you can have things like the purple one where it's higher for some energies and lower for other energies. And this means that even though we don't, we only measure, we don't know what the true flux is at IceCube, what we would get, for example, in the purple case is a hardening of the spectrum followed by a softening of the spectrum. And so this is something you can look for. All right, so there's a bunch of parameters here, and we have plots of all of them. They're in the backup slides or in the paper, but I'm just going to briefly summarize what these different things do. So as you change the gamma, which is the initial source spectrum, a harder spectrum that is, a smaller gamma leads to a larger regeneration component than a softer spectrum. And this makes sense because if the spectrum is very soft, when neutrinos are regenerated at lower energies, the contribution is quite small. Well, if it's hard, then the regenerated neutrinos contribute possibly quite a large amount. The next parameter is M1. This is the absolute neutrino mass scale. If M1 is larger than around 0.1 eV, there's a larger regeneration component, and this is because in this limit, neutrino masses are closer to degenerate, and the phase space is different, and so the resultant decay products have most of the same energy as they started with. Basically, less of the energy goes to the phi particle, the moneron. And then for different couplings, for these different textures of this matrix, as we saw before, you can get very different structures, and in addition, in a flavor-dependent way, which I haven't shown, but will affect oscillations, will affect the signature for IceCube. We also investigated a bunch of other things, like what is the redshift evolutions of the sources. This doesn't affect things too much. We also looked at whether or not you have scalar interactions or pseudoscalar interactions or both. This doesn't affect things too much. We also looked at whether there's only new to new or only new to new bar or both. And again, this doesn't affect things too much. So those last two are related to whether or not neutrinos are moneron or Dirac, but we treated this in a more, even more general way than that. So what does IceCube bring to the table? They measure the energy of neutrinos fairly well. They measure the directions often quite well, and they measure the flavors only a little bit. But the fact they have all three of these gives us a nice handle to check for new physics like this. And we're going to focus on energy and flavor, but it's interesting to think about other examples where different combinations of these come into play. So IceCube has a tension. I'm using this word a little bit loosely here, but they do say this in some of their papers, so I think that gives me the liberty to take this seriously. In the spectrum that they measure for their tracks and their cascades. So the tracks are muon neutrinos, and the cascades are electron neutrinos and tau neutrinos. It's a little bit more complicated than that, but the details end up not making that much of a difference. And the difference in the spectral indices is 0.54. And it's harder for tracks than cascades, which is important. Within the standard model, you might wonder how much of a deviation could you get based on astrophysical uncertainties. And I've checked a number of cases, and it's very hard to get anything bigger than around 0.2. So 0.54 is a pretty big difference from that. It's not, it's not hugely significant, but it's something interesting to pay attention to as more data comes in. So in the standard model, in a vanilla sense, you expect the spectral indices. So this is the spectral index we measure at the Earth as a function of different couplings. In the standard model shown in green, of course, it's just constant as whatever you started with. But if you include neutrino decay, you can get some deviations. And that's what's shown here. This is for neutrinos coming from just a fixed redshift, which is a good approximation, and for a given spectral index. And so then we can compare the track to cascades shown in blue and orange, and we can see that if the coupling is right, basically, then you can get a fairly significant shift in the spectrum that is observed at the Earth. And what I've done here is I've fitted the spectra we saw earlier, which have various shapes, to a single power law within IceCube's region of interest. And you can get some kind of a shift here. And for context, this shift up here at higher couplings comes from the solar side, and this one's at the lower couplings comes from the atmospheric side. So then we can look at the actual IceCube data and ask ourselves, what parameters describe this shift? If we take this tension seriously, what parameters might this lead to? And at a delta chi squared of a little over 10, we find that a coupling of around 10 to the minus 6 is preferred over the standard model. And this corresponds to a spectrum at the source of around 2.7, 2.8 or so. That is to say, the initial spectrum was a bit softer, and neutrino decay made it a bit harder to match up with the observations of IceCube, which, for example, the track spectrum is quite hard, around 2.1. Oops, did I do that? Can you see my slide still?
Sorry, your slide. Now your slides disappeared. I don't know why.
Okay, I don't know either.
Maybe you can start sharing again your screen.
Yeah, sorry. I'm on the last slide anyway. Hopefully this works. All right, can you see this?
Yes. Okay.
Okay, good. Sorry. All right, here's the conclusions. I'm right at the end. So neutrino decay can be probed in a huge range of experiments, as I showed, from atmospherics to cosmology to astrophysical neutrinos. Visible neutrino decay, not only do you have the depletion, but you have this regeneration, which leads to very interesting phenomenology. And this depends on not only the spectrum, but also things like the texture of the couplings and the neutrino mass scale. And you get a huge range of different things as you dial all kinds of knobs. ICHEP has unique sensitivity to this because of the fact that it can measure all the different flavors. And the track and cascade spectrum is well described in neutrino decay if we take this seriously. And the final point, which I didn't really discuss, is that assuming the mass ordering is normal, which maybe we don't know that as well as we thought we did a few weeks ago, but neutrino decay predicts that the track spectrum is harder than the cascade spectrum. It can't do the other way around. So if the mass ordering is normal, and neutrino decay was happening, we would have to see the kind of a thing that we are seeing at IceCube. And we couldn't get the other way. So that's it. Thank you very much.
Okay, thank you for the talk. Are there questions, comments? Yes, I see a question by David, please.
Hi, this is David Karate. Hi, can you hear me?
Hi, David. Yeah.
Yes.
Hi. My question is on the visible decay scenario. I was just wondering if you might see your electron because of the decay that's involved.
I couldn't quite hear all of that, but were you asking about, well, can you say that again? The audio cut out a little bit.
If the direction of the neutrinos you're detecting would shift as
Yes. So this was investigated in a number of papers, but there's one by Tommy Olson and friends. And in principle, there is an effect by this, yes. For these hive energies, the effect is exceedingly small. And in addition, for this, for the IceCube neutrino flux, we don't know where they're supposed to be coming from in the first place. So if they shift directions, that doesn't really do anything for us. But yeah, the people have calculated this, but I think at these energies, it's not going to be a big effect anyway, even if we thought we knew where they were coming from.
Thanks.
Yep.
So maybe I can ask a quick question. So I understand that you are looking at the spectral shape of the signal. Now my question is, how well is the standard model known? I mean, how robust is your signature with respect to uncertainties in the standard model shape?
Yeah, so that's a great question. So first of all, there's uncertainties in the oscillation parameters, which we know, but that's not going to change the relative spectrum of the different flavors. If we assume neutrinos come from full pion decay, then to a very good approximation, the spectrum of all the flavors initially is the same. Now, if you do damped muon decay, you can get a small shift, where that is where the pion decays to muon neutrino, but not the other two flavors, the other two neutrinos. And if this happens in the middle of IceCube's energy range, you can get a signal, you can get a change in the spectrum that's different for tracks and cascades. However, because oscillations and theta 2-3 is large, the effect from this is very small, and that's where the 0.2 number comes from. I didn't really show that here, but it's hard to get delta gamma bigger than around 0.2 from any standard model thing. Yeah.
Okay.
We can talk about that later.
Okay, very good. So I think it's time to conclude. I would like to thank all the speakers for the great talks and keeping the time. And so we conclude the session, and I understand that now there is a short coffee break, and the session continues at 17:30, so in about 12 minutes or so. Thank you, everyone. Goodbye.
Hi, Thomas. Can I ask a question? I'm the next speaker. Xianguo.
Yes, please.
Yeah, I see in the chat window that someone asked whether we would like to test the audio and the sharing during the coffee break. Is it supposed to happen now or right before my talk?
Well, I guess I think the time would be now, no, because during there is not much time left. So maybe it's the best thing to do it now. Right?
Okay. Could you test for me? I'm going to share. First, make it full screen, and then now I'm going to share. Oh, no, this is not the correct one. Sorry. Do you see my screen?
Yes.
With my talk front page. That's right.
Yes. Yes.
Okay, that's great. Thanks a lot. Then I don't shut it off. I just keep it like that. Is that okay or?
Well, maybe you stop sharing. I don't know if there will be some other things, but.
All right. Okay, I just stop and then I will share again. Thank you.
I think that's better.
Okay, thank you. Talk to you later.
Tomasz, can you Tomashi?
I think he left. Also,
Hi, this is well, there's a big echo. This is Ryan Hobbs, but I'll be carrying the next session.
Tomashi?
Okay, so I have 30 after the hour, so we should get started. And just a reminder, the talks are blocked for 15 minutes, and that includes time for questions. So we have a very long session, so we'll have to keep to that very tightly. Up first is Xianguo Liu about MINERvA interaction physics with low energy data. So go ahead and start sharing when you're ready.
Okay, thank you. Let me share my slides now. Can you see it?
Yes, looks good.
Okay, thank you, Peter. So first of all, I would like to thank the organizers for putting up this nice virtual environment. This is Xianguo Liu from University of Oxford. On behalf of MINERvA, I would like to present to you our recent low energy results. Neutrino oscillation measurements like T2K, Hyper-K, Nova, and DUN, they all rely on near detectors to constrain the systematic uncertainties from the neutrino interactions. And MINERvA experiment is a dedicated experiment to measure neutrino interactions and constrain the oscillation measurement. This is our scintillator tracker. It is surrounded by kilometers and followed up by the MINERvA near detector. Our tracker is non-magnetized, therefore it can identify charged particles and also measure particle momenta. So in this case, you can jot electromagnetic showers. Muons from charge current interactions are measured by the MINERvA near detector. So in MINERvA, actually we can measure different interactions depending on the energy momentum transfer. Here we call them Q0 and Q3. We can have the quasi-elastic scattering and resonant production, and also deep inelastic scattering. The intensity of all these interactions depends on the neutrino energy, as is shown in this plot. And in the lower plot, you can see the flux compression between T2K, Nova, DUN, and MINERvA. For the MINERvA low energy flux here, we are dominated by pion production, and this is the focus of my talk today. In our previous study, we found that in order to describe our data, the model has to have this so-called 2p2h-like enhancement. What we did is the following. We measured the available energy. This is the sum of the energy of the all final state particles. We use it to approximate the energy transfer Q0. And this is the energy, this is the number of event distribution we measured, and we compared to the nominal model. You can see the quasi-elastic comparison, the resonant comparison, and most importantly, the nominal 2p2h comparison component here. And correspondingly, this is the overall prediction from the nominal model. You can see there is a big deficit from the model. And in order to fit data, we actually have to increase the 2p2h contribution. And the enhancement is 50% overall and can go up to 2 times in the deep region between the QE and resonance contribution. We do this fit to neutrino data, but then we take the fit result directly and apply it as a prediction for anti-neutrino. This works very well, surprisingly. So the thesis of this talk is to use transverse kinematic imbalance, TKI, to study nuclear effects in neutrino interactions. The idea is rather simple. Suppose we have a stationary nucleon target, then in the plane that is transverse to the neutrino direction, the electronic system and the hadronic system are back-to-back. However, with the nuclear target, because of nuclear effects like the Fermi motion, functional interactions, 2p2h pion absorption, you name it, there are energy momentum transfer inside the nucleus. And therefore, on the transverse plane, we don't see the balance muon and hadronic system anymore. So let's first take a look at the MINERva's measurement for the QE-like channel on carbon. This QE-like means that in the final state, we require there's no pion. And this channel actually help us to probe the neutrino interaction on neutron going to a muon and a proton. Just consider this slide as the transverse plane to the neutrino. And this is the muon PT vector. This is the proton PT vector. And this one is what we usually call the missing PT. And this is a vector, in fact. And the delta alpha T variable is the direction of this missing PT vector. Furthermore, by assuming the nuclear random after the interaction is the carbon-11, then we can calculate the full momentum, full missing momentum. For QE, this full missing momentum can be interpreted as the Fermi motion of the interacting neutron. It is related to the missing PT by a small correction. So in the first order, we can consider this Pn as the missing PT. On the right-hand side, you can see the theoretical prediction for this Pn variable. The model we use here is the MINERVA Twin Genie with the 2B2H enhancement that I just introduced to you. You can see for the quasi-elastic contribution, that is the Fermi motion peak, and the interactions, all the other interactions are in the tail region. And the 2P2H lag enhancement lives in the region somewhere between the peak and the tail. Now let's compare the data to Monte Carlo. So for the moment, let's focus on the same Monte Carlo as we just discussed. This would be the stacked colored histogram here. Comparing to data, actually we see that exactly in the region where we had the 2P2H lag enhancement, the data seems to be asking for more enhancement. This is very interesting. And now in this slide, let's focus on the measurement of the delta alpha T variable. In this plot, the black points are the MINERVA measurement. The red points are the theoretical measurement for us to compare to. And this delta alpha T is the direction of the missing PT vector. So if this vector is aligned with the QT vector, this delta alpha T approaches 0. And in this region, it is dominated by quasi-elastic interaction. As delta alpha T increases, we can see from this cartoon, this missing PT vector actually is pulled back by dissipative dynamics. This includes final state interactions from quasi-elastic channel and also pion absorptions, inversions, and DIS. They also include the missing nucleon dynamics from the 2P2H. In fact, if you look carefully, all these dissipative processes live in the tail of the PN distribution. They are the large missing PT part. And we all know the resonance production and DIS and 2P2H all have energy dependent. This actually gives rise to the difference between the MINERVA and T2K results difference. We have just seen the TKI measurement in the quasi-elastic channel. However, the same trick can be played for the inclusive Poiseuille production. The idea is the following. We, in addition, measure the Poiseuille kinematics and then combine it with the proton kinematics to form the hadron kinematics. Once the hadron kinematics is formed, the math is the same. And experimentally, in MINERVA, we measure inclusively Poiseuille production, namely in the final state, we require muon proton and additionally 2 shower to reconstruct the Poiseuille and then get the kinematics fully. Here is a comparison between the theory and data. Since this is the first time to show this data, let's have a closer look at this. On the upper plot, we have Neutron and Gini predictions. This curve is Neutron prediction without FSI, and this one is with FSI and with the global Fermi gas initial state. Here, the neutral prediction and Gini prediction both are with FSI and with local Fermi gas initial state. Now, let's have a look at the lower plot. The data set is still the same, but then we have a different Y scale. And this is the prediction provided by Gibbel. Interestingly, in the Fermi motion region, when the Pn is small, our data sits somewhere between the local Fermi gas and the Gibbel prediction. Now let's have a look at the large missing PT part. Surprisingly, all models seems to be doing okay to describe the data. And one more important point to notice is that in this sample, we only have resonance production and DIS. There is no quasi-elastic production significantly, not to mention 2p2h. Now we are in the end, we would like to compare the two TKI measurement in MINERVA. One from the quasi-elastic like channel, the other from the partial measurement. What is shown here are the normalized distribution of the cross-section. And on the left is the PN distribution. On the right is the delta alpha T distribution. Since both channels actually are probing the neutrino interaction on neutron inside the carbon nuclei, so the initial state should be the same. And in fact, this is what we have observed. What you can see is that in the small PN region, where the Fermi motion peak is supposed to be dominant, we have the same shape for quasi-elastic-like sample and for the inclusive partial sample. This is interesting. We are probing the same thing. And in the large missing PT part, we can see that the pi absorption actually is doing different things for the two samples. For the pi production sample, pi absorption will reduce the open pi production. However, pi absorption at the same time will increase the absorbed pion contributions to the QE-like event. So now we see a consistent size in the tail. This is rather surprising. Now let's have a closer look to the dynamics of this event by looking at the delta alpha T, because as we can see previously, the non-flatness of this delta alpha T distribution tell us about the dissipative dynamics of the interaction. And surprisingly, again, in this case, we do see the two samples do display the same internal dynamics, namely how the missing PT vector is pulled back. Even though the QE-like interaction and the pi cell production have very different dynamics, the strength seems to be the same in this case. So here is my summary. In this talk, I have presented a selected topic from our low energy data set. The TKI, the transverse kinematic imbalance result from both the QE-like event and inclusive partial measurement are presented. Just to wrap up, in our QE-like event, it seems to suggest that we like to have even stronger 2p2h-like enhancement. On the other hand, for the inclusive partial production, there is a mismodeling or overall at the Fermi motion peak, and the large missing PT region is reasonably described. For the shape comparison between the two measurements, we have rather similar dissipative dynamics at the large missing PT. So in MINERVA, actually we have more TKI measurement. For example, for the one that is on the binding energy, please refer to this paper. And for our medium energy result, please stay on to Heidi's talk. That's all. Thank you.
Thank you, Xianguo. That is pretty much the full time of the 15 minutes. So I think we'll have to move on in order to stay on track. If anyone has an important question, they could post it in the chat and we can try to come back if we have a moment later.
Thank you, Peter.
Let's see. I think Heidi Schellman is up next. Yes. Go ahead when ready.
Okie dokie. So, well, thanks to the organizers for organizing this on such short notice. So I'm going to be talking about newer medium energy data from MINERvA experiment. And so you've seen in great detail what we can do with a reasonably small sample. So now we're starting out to look at our larger sample. So of course, the main motivation for this whole session is, why is there more matter than antimatter in the universe? And to some extent, trying to figure out what's going on with neutrinos in the universe. If we're looking at CP violation, we need to know the difference between, we want to study the difference between muon neutrinos oscillating into electron neutrinos, and the same process for antineutrinos. And the thing you see is that if you do a simulation of this with some CP violating parameters, you see that there is a difference in the neutrino oscillation probability for muon neutrinos going to electron neutrinos and antineutrinos going to anti-electron neutrinos. But in order to really understand this, you have to understand both the relative rates for these interactions and the energy scale. If you get the energy scale or just can't measure the rates the same, you have a problem. So you want to look at processes that are similar or give similar results for both. So the things we need is, there's two ways to estimate the energy of a neutrino interaction. One is to basically sum up all the final state energy. That works well in some processes, but not so great for antineutrinos. Or you can use the quasi-elastic scattering kinematics that Xianguo talked a lot about in the previous talk for a subset of the events. So what you end up with is being able to estimate the neutrino energy. If you know the muon angle and its energy, you can, and some estimate of the binding energy, you can actually use that to estimate the neutrino energy. So this is a problem I give to my undergraduates, and they hate me for it because it's actually not that easy. Of course, the problem is, it's not just an undergraduate kinematics kinematics study for undergraduates. It also, we're dealing with real life nuclei. So you have Fermi motion, you have screening, you have these 2p2h processes where you don't just hit one nucleon, you basically hit a pair of coupled nucleons, and so you get two particles coming out. You also have interference effects. Once again, neutrino can come in, hit a nucleon, produce a resonance, but that resonance, the pion from the resonance gets absorbed, so it looks like it's a quasi-elastic scatter, but in fact, the actual interaction happened at a larger mass. Or you can have a real event happen and knock out a pion. So you can get confusion between a real quasi-elastic scattering and a non-quasi-elastic. But of course, we're doing quantum mechanics here. We can't see what's going on in the nucleus, and all these things could interfere with each other. So in fact, what we do is we define the signal based on the signature outside the nucleus. So our signature is going to be defined by looking outside the nucleus. And for example, for an antineutrino, you'd only have a neutron and a muon. But for a neutrino, you'd have one charged muon, any number of protons, so you can see the 2p2h type effects, no pions, low additional recoil activity. And we're allowing any number of protons so we can include the more interesting 2p2h contributions. Okay. So just looking at this, if you're looking at the energy distribution, this is a Gini simulation showing the energy distribution broken down by whether or not it shows up as one of these backgrounds where you've actually confused, or the underlying process that looks like a QE-like, in other words, no pions final state. You can see a real quasi-elastic scattering off a nucleus actually does have a nice symmetric distribution, which is only generated by the Fermi motion. But the moment you start adding 2p2h, you see that you get a tail on the low side. You're underestimating the energy. Other backgrounds make it even worse. And in fact, the ones that aren't even really QE-like at the generator scale, but show up as such in your detector due to detector effects, really skew it low. So what we're trying to do, in order to, if we want to understand our energy scale, we have to understand the relative rates and of these various processes in some detail. Otherwise, we're going to have a significant energy misestimate. So once again, this is the MINERvA detector. It ran from 2010 to 2019. I'm going to be talking about data from the active tracker region, which is made up of these scintillating triangles that are a couple meters long, and that tracker is surrounded by calorimetry, and then there's a muon tagger at the back, otherwise known as the beautiful near detector that does momentum analysis on muons with momenta of above about 1.5 GeV over C. Okay, so here's our experimental signature for a quasi-elastic neutrino scatter. So neutrino comes in, you see the muon coming out, you see the proton coming out. If it's a nice clean signal, you don't have too many of these isolated clusters, which are just sort of random neutrons and junk. There's not pi zeros floating around. And you don't have any tracks that are consistent based on energy loss with the pion. So we identify our pi pluses by Michel electrons. We also use some DEDX to tell the difference between protons and pions. We look for pi zero decay showers. And in fact, if there's multiple charge tracks, we also have to figure out what's going on. So first we took some data. This is just to show you the size of the sample. Xianguo was showing you the data from the low energy data, which was taken before 2012. And we've run since then with a higher energy beam, but also with a lot more protons on target. And so you have a substantially larger statistics to work with, albeit at a higher energy. In antineutrinos, in fact, the increase is even greater because we actually took much more data in antineutrinos. And I'm going to show one result from that later. But this is showing you the difference between the data samples. So there's a lot to come. We do absolute flux normalization by using neutrino electron scattering. So we actually have around 1,000 of these direct scatters. The neutrino comes in, scatters through nuclear current off of an electron, atomic electron. And in that case, the kinematics are incredibly far forward. So you can tell the difference between this and, for example, the residual electron neutrino content of the beam scattering off nuclei. By measuring the electron energy spectrum, you can actually get an estimate, not just of the total absolute flux, but something about make certain you're checking the energy dependence. If you apply this to our data as a constraint, it actually reduces the overall neutrino flux estimate by something on the order of 10 to 12%, but also significantly, because of the constraint, actually significantly reduces the flux uncertainty. So you get a different, but also better constrained total cross-section measurement. So now let's actually look for this signal. We're looking for neutrino scattering quasi-elastic. So here's a typical event in MINERvA. This is probably a recoil proton. Is this a pion? Is it a proton? This is the muon, nicely identified. Is there a neutron or a pi zero floating around? So what we do in order to estimate the background is we define sidebands by the number of isolated clusters, if it's less than 2 or greater than 2, and the number of Michel electrons that are identified. We take these sideband regions, we fit them to a distribution of signal and background, and we take the signal region and do the same thing. And from that, we can determine the background fraction due to all of these processes in our data and subtract it. We end up with this as our final result. This was published in PRL earlier this year. 825,000 events after background subtraction. Therefore, the errors you see here are almost 100% systematic rather than statistical. And what's shown here is the MINERvA Gini V1 model, and then as a total curve, and then the various components that go into it. So you can see quasi-elastic in green and 2p2h in purple. You can see that there's regions where the 2p2h is actually dominating over the quasi-elastic in our tuned models. So let's look at this in more detail. This case, I'm looking at the Q-squared distribution. And so this is the Q-squared distribution, and we're comparing it to different models. Once again, the red is the MINERvA Gini model with all our tunes. The blue is just straight out of the box, Gini 2.12.6, and the rest of these curves are actually the contributions that make up the MINERvA prediction. So you can see where the various curves are important. And if you look at this in more detail, what we're doing now, because on this previous slide, you'll notice it's covering 3 orders of magnitude. So looks great, doesn't it? Okay, so but if you actually compare by doing a ratio to the base Gini 2.12.6, you see that the data tends to lie below the simulation at very low Q squared and actually at very high Q squared. And we'll point out that we are actually going out to Q squared of close to 10 in these curves. So here we compare it with more models, including a new version, better improved MINERvA tune, which tries to do something about this low Q squared tail, but still hasn't gotten there. So there's still significant discrepancies at low Q squared for all the models. So once again, we're doing what Xianguo was doing. We're looking at other variables. In this case, we're studying the triple differential cross section, since we have enough statistics, by looking at the sum of the hadronic energy by summing up the kinetic energy of all the identified protons in the final state. And that's close to this standard scattering variable omega. This is some electron scattering data showing the contributions in an omega distribution from quasi-elastic and delta production, and then the 2p2h down here. And you can see that you need the 2p2h in these data also to explain this dip in the middle. So here's some preliminary data. We haven't finalized the analysis on this, but this is what we do is we look in bins of PT and p parallel. So this is a bin of p parallel, which is basically near the peak of our beam distribution. We're looking at different PT bins at the visible energy, essentially the recoil energy. And what you see is, once again, quasi-elastic in green, the 2p2h in a sort of purpley color. And although it looks nice, in fact, there are substantial discrepancies, especially at the larger visible energies. And so these studies are ongoing, and we'll have more results for you at the next Fun conference. Another preview is we are actually doing the same analyses for antineutrinos. This was actually shown in a poster session at Neutrino, is the event rates, just to show the event rates for antineutrino quasi-elastic events. And we have 477,000 of these events to study. This is just two-dimensional PT distribution in bins of neutrino momentum, parallel momentum. So once again, you can see the data are slightly higher than the simulation. Reasonable agreement, but given the level of statistics we have, we should be able to get a lot more information out of this. We also have inclusive measurements, which, because of the flux uncertainties being less and the higher energy beam, allow us to go out to higher p parallels. So way out in p parallel, and also divide up and have additional PT bins. So we're going out to PT of close to 4 in this case. So once again, these are just a comparison of event rates between the data and the simulation, but we'll be able to publish cross sections on those as well. So here's my conclusion. We are going to have, out of the medium energy data, we already have published some cross-section measurements. Several more are coming out. We'll have lower flux certainties and much higher statistics. So this allows us to do detailed 3-dimensional measurements of things like the visible energy and this transverse kinematic imbalance. We are also working on nuclear dependence by looking at our lead, iron, water, and helium targets and comparing them to the carbon targets. We are working on neutron detection so that we can do some studies of what neutrons look like. And we have enough high W events that we can actually do some shallow and deep inelastic scattering studies. And I'll point out that we have stopped taking data in 2019, but we have an incredibly active and young group doing data analysis now, and a very active data preservation project that will make these data valuable for the long term. So thank you to everybody for your attention.
Thanks, Heidi. Yeah, that we're again at the start of the next block, and I think we must keep to time in order to stay within our total time. So I think we'll have to move on. And there is this Mattermost chat system available for posting questions and interacting. I think we're going to have
I will
to
stop sharing.
carry on. Let's see. Up next we have Raquel Castillo Fernandez with recent measurements from MicroBoon, and you can start when ready.
Okay, thank you very much, and thank you for the organization to invite it for this talk. So I'm going to present the result cross sections results from MicroBoon. I would like to remember that MicroBoon has several talks in this ICHEP conference. So we have 4 talks in the neutrino physics sessions, but I also want to invite you to see the other sessions talks that we have in searches beyond the standard model and the operation, performance, and upgrade of the present detector sessions. So MicroBoon, the main goal is to investigate the low energy excess or the electron versus gamma excess anomaly observed in the LSND and MiniBoon experiments years ago. You should see the big catalyst talk that he will be focused on this topic. This talk is, however, focusing on the neutrino argon scattering cross-section measurements. And we have another talk from Ralitza explaining the R&D that MicroBoon is provided for the liquid argon time projection chamber technology used in other experiments, like, for example, DUN. MicroBoon is the first phase of the short baseline neutrino program at Fermilab. It's important to note that it's the first big liquid argon time projection chamber operating in the US. We have developed the first automatic reconstruction in a LRTPC. We have the largest neutrino argon scattering data, and we have the longest LRTPC operating in the world. These are very, very important things to know, because we have put a lot of time to understand the detector and to understand the physics. The detector is located at the same location as the MiniBoon experiment in the taking data from the booster neutrino beam, the BNB. It's an almost pure muon neutrino beam, very few electron neutrino contamination. It is the neutrino beam is on axis, a little bit less than 500 meters from the neutrino production. And we have excellent particle identification capabilities, so we can perform additional ray process searches. So you should see Owen, Jeon-Jae, and Pavel's talks, some of them today, tomorrow, and then the 31st of July. The main design of the detector, it has 3 different systems. The principal component is the liquid argon time projection chamber, but we have also a photon detection system that will help us to identify cosmic background. We have also a cosmic ray tagger, also help us for the cosmic ray background. I will focus on the LRTPC principles. Our LRTPC has 86 tons of active mass of liquid argon, and we are operating near surface, meaning that one of our main challenges is this cosmic ray contamination. LRTPC are excellent on providing very good topology and calorimetry, meaning that we can reconstruct tags or showers from in a millimetric scale resolution. We have a full angular coverage, and we have particles observable from very low kinetic energy. So you can see from the cartoon, when we have a charged particle entering the detector, it ionizes with the argon, and these electrons produced by ionization, they go in the opposite direction of the electric field toward the wire planes. Here are not up to scale. The distance plane to plane is 3 millimeters, and in each plane we have thousands of sense wires, and the distance wire to wire is 3 millimeters as well. We can observe in these sense wires this image, as you can see here. This is from the correction plane. The x-axis represents the wire number, and the y-axis the drift time. And so you can observe these objects, and we perform the particle reconstruction and then the identification. First, we can discriminate between a charged particle or a track with respect to an electromagnetic shower. We can start in discriminating cosmic ray activity, but looking for for crossing tracks. But we perform a lot of, we develop a lot of work in particle identification. As I said, we have the lowest particle energy threshold with respect to any other neutrino accelerator by set experiments. So we have been able to observe protons from less than 50 MeV in kinetic energy at the Fermi momenta. We can observe proton multiplicity, and what we do is to reconstruct the energy loss by ionization by following a Bethe block approach. Here you can see an example of an even display where you can see a candidate muon, a minimum ionizing particle. So the color of this even displays, as more blue is less energy loss or less charge deposit. It starts to be green up to red. It's the most energy loss. So you can identify black pigs. You can identify high ionizing particles like protons. So it's a very detailed detector with very fine granularity. Why this is important? Why is it important to study neutrino scattering physics? My colleagues from MINERvA, they already gave very nice talks. So this is fundamental for the oscillation program. When we measure oscillations, we don't know how many of these neutrinos has oscillated when we detect, and we want to measure the probability of these oscillations. What we measure in the detector is the flux time cross-section. So we need to have a first estimate of the flux, but we need to measure very precisely the cross-section of these neutrinos for the signal events. One thing to note is that these probabilities are in function of the neutrino energy, and the neutrino energy is not unobservable because the neutrino per se is not directly observed. We don't have a monoenergetic neutrino beam, so we have to infer the neutrino energy by the observation of the final state particle kinematics. We also need to subtract the background, so we need to measure as many neutrino cross-sections as possible for all the flavors and all the interactions. Here in the cartoon, there are the schematics of the most common neutrino interactions, the quasi-elastic, resonant, and deep inelastic scattering. And as you can see, there is not a clear difference at which energy some interaction happens, quasi-elastic with respect to resonant scattering. There are some other interactions as Meson-Exchange currents. Some of my colleagues, they refer as 2p2h, I will refer as Meson-Exchange current. And they have more complex interference with the other channels in terms of neutrino energy. In the top of that, we have very little knowledge of neutrino cross-section because we have very few data, and even less in argon. So our cross-sections are very small. They are weak interactions, and we are not a collider experiment. We really have very little data. For the purpose of microbun, that is looking for possible neutrino oscillations or possible signals at low energies of these neutrinos, we have these 4 different channels that we are investigating, and you should see later today the talk from David Caratelli. He will focus on these 4 channels. I will focus in the other channels that we are using for neutrino argon scattering, some of them, that we use to understand neutrino event generators, or the physics that involves the particles produced after a neutrino interacts. So the main signal is a muon neutrino charge current inclusive interactions, meaning that you have a muon neutrino interacting with the nucleus via double view boson, and you can have any particle in the final state accompanied with a negatively charged muon. So during this year, we have produced a result from on this measurement, muon neutrino charge current, single differential cross-section measurement in argon. We are moving into a double differential for this measurement. But we can already observe comparisons of our data in terms of muon kinematics, muon momentum, and the angle of the muon with respect to the neutrino beam. There are some places where the Monte Carlo can explain our data. There are some regions where it is more challenging. And one important thing to note is that this is not a new analysis. This is an updated analysis. We published 2 years ago a measurement in the same channel, and as you can see from the table, we were dominated by uncertainties in the detector response. So one important thing to know from today, from the last ICHEP conference, is that we have been developing an exceptional campaign to model and calibrate the detector, and also to understand the argon properties, that this was non-trivial. And this was a lot of work, mostly driven by students, and they deserve a lot of acknowledgement for this great improvement. You can compare these results from 2020, from this year, from the results on 2018. And one of the things that you know that you can see from these plots is, for example, the background, the dominant background, cosmic background, this dashed histogram is mostly reduced in the new analysis because of a better understanding of the detector, also the signal processing and all the work that has been developed. We observe as well a better explanation from the Monte Carlo to the data. So the different campaigns for the calibration and signal processing, they help us a lot. In addition to this, it was some additional tuning for the neutrino event generator that we used. You can see that in 2018 we were using GeneV 2, and in 2020 we were using GeneV 3 with some additional tuning. And it's good to mention that the tuning it was using T2K pion-less data, CC0 pion data. So as you can see, the improvement is basically from the positive cosine of the angle of the muon. But for example, in the backward going region, we are still the same discrepancies that we observed in 2018. And this is very interesting because it's an apples to apples comparison. It's still data from microboom, and it behaves the same. So there are many different physical reasons that can explain that. One interesting one is that this could be resonance of DIS, that they tend to be more backward going component that in a quasi-elastic regime. There is also to note that the different detectors, the different experiments, they have different acceptance. So microboom has a full angular coverage, and when we are using, for example, T2K data, didn't have for the data that we use for this tuning the full angular coverage. So there are many different components that are very interesting to investigate. Moving forward, we did more exclusive measurements due to the improvements on the particle identification, exploiting the resources that offers the liquid argon time projection chambers. And I'm going to talk about muon neutrino charge current with one proton in the final state. So this is a subsample of the previous data set of the inclusive sample. In this case, we observed the presence.
Sorry, Raquel, you have about 90 seconds left, so you may have to go a little faster.
Okay, sorry. So we observed the presence of a negatively charged muon and a proton in the final state. I will try to go very fast. You can see the result. It has been published in arXiv and submitted to PRL, and we have major discrepancies in the most forward bin. We published as well on PRL muon neutrino charge current with one single neutral pion in the final state. This was published in 2019. Now, due to the new improvements, we have updated analysis, and you should see the talks by Mark and David later today. So I cannot go to details. We have as well ongoing an analysis on neutral current with one single proton in the final state. It means a neutrino interacting with the nucleus, and you only see a proton in the final state. This is a very challenging analysis because you have to only see one single proton. It can be very low energetic, and you have to reconstruct properly the direction of the proton. This analysis is interesting to study the strange axial form factor by looking at the low momentum transfer of these interactions. And just to finalize, you will see later today after my talk, more studies on electron neutrino charge current inclusive analysis. In this case, we have two different data sets from two different beams. Today, you will see the ones from the booster neutrino beam, that this will be covered by Wouter. And this is very important to understand the difference in the neutrino scattering model from muon neutrino, that is our main signals, our main data sets, to the electron neutrino, that is where we are looking for anomalies. And it's not straightforward to extrapolate this scattering processes from one flavor to the other. Also see the big characteristic for the exclusive channels in Electron Neutrino later today. And just to mention that there are several analyses that they are in progress and to be shown very soon, exploring the nuclear structure, looking much more deep into the most quasi-elastic channels, so no muon, only one muon and no protons in the final state observed by the detector. Pion production, a study of monoenergetic neutrinos using count decay at rest. Also constraining uncertainties in the electron neutrino, as I mentioned, from the other beam that we observe, and searches for measurements that are useful for backgrounds in proton decay, such as the neutrino count production. So just to summarize these 5 measurements that we are already producing, we made the first double differential cross-section in argon from muon neutrino scattering.
I think we'll have to stop here. We're a minute and a half over. But I think the conclusion can stay there for a second as we let's see, move to Mark Ross-Lonergan, who will continue with a specific channel in microboon. Yeah, so maybe you can swap over the share. Yeah, I do encourage speakers to try to aim for 13 minutes or so we have some time for interaction perhaps. Go ahead when ready.
Great. And can you confirm you both see my screen and hear my voice?
Everything looks good.
Great. So yeah, thank the organizers for the invitation to speak here. And I'm going to continue with the microboon theme. So remember everything Raquel just said. But I'm going to be focusing on neutral current pi0 measurements. So most of the motivation for this study of neutral current pi-zeros does come from our flagship analyses to investigate the mini-boon low energy excess. As a lot of people have heard, the mini-boon observed a electron-like excess at low energy, but because it is a oil Cherenkov, it couldn't tell the difference between electrons and photons. But as Raquel has shown, microboon can. And we have multiple ongoing analyses to select high purity single electron and single photon samples. And that's the topic of David Cartelli's talk later today. So please do stick around for that. But putting aside the LEE, motivation for studying pi-zeros, you don't really need much because neutral current pi-zeros are not very well understood on argon. So as Raquel said, we use Genie version 3 in microboon. And the majority of the neutral current pi-zeros that we have, about 80%, come from resonant production of a delta baryon. So neutrino comes in, interacts neutrally, excites a nucleon up to a delta baryon, which then decays back to a nucleon and a pi-0. The remaining 20% come from a multitude of other sources, including coherent pion production when the neutrino interacts with the whole argon nucleus. There's a small amount of deep inelastic scattering, although at our energies it's not huge. And then there are pi-zeros, which were not created in the initial neutrino interaction, but a result of final state interactions in the nucleus. So a nucleon re-interacting with another nucleon before it leaves the nucleus. However, for most of these, for neutral current, there's very little data on argon, and there's very, very large uncertainties in Genie as a result. One of the biggest data sets for neutral current pi-zeros on argon comes from Argon Neut, but it's an inclusive measurement, so it's very hard to disentangle the different features, and it is stats limited. As an example, the coherent normalization in Genie has an assigned 100% error. Several important cross-sections for FSI have errors up to 50%. And even the resonant production, which is the bulk of the neutral current pi-zero, has about 20% uncertainty in the axial mass. So it's clear that we really need more data on argon, although maybe it's not so clear as to why this is important to the LE in particular. But if we take a look at the main production channel here, which is the delta resonance to make a pi-zero, this isn't the only decay that happens. In fact, at about a 0.6% branching ratio, the delta can decay radiatively into a single photon and not a pi-zero. So this is a neutral current delta radiative decay. And this process has never been observed before in the neutrino sector. So this is a standard model source of single photon events. And as a result, it is a possible explanation for the mini-boon low energy excess. And measuring this channel is the goal of our first photon analysis in microboon. So in this analysis, we basically have two selections ongoing. We have the case, well, they're both looking for delta radiative events, but the first case is where we have a proton alongside our single shower. So this is the case where it's a delta plus decaying to a proton, mostly, although FSI does interrupt things. So we have a single track that looks like a proton, a gap, and then a nice shower. So we call this our 1 gamma 1p selection. And we also have one without a proton track, which is just looking for a single lone shower in the detector with no hadronic noise around it, which is a tricky channel. Now, cartoons are good, but it's better to look at real data. So here's a neutral current single photon candidate event in microroom. This is real data. So we have the neutrino presumably coming in here. We have a small, short, highly ionizing proton candidate. We have a large gap and then an electromagnetic shower, which is our photon candidate pointing back relatively well to the vertex. We can also look at pi zeros. So this is a very nice neutral current pi zero event in microboon, where again, we have a presumed neutrino interaction at the vertex here, a highly ionizing short proton track. And now we have 2 showers coming from presumed pi zero decay, where the photons propagated a short distance before pair converting. And we've reconstructed both showers quite well. So in this case, there's not a problem for distinguishing these 2 nice events. However, the distance that a photon travels before a pair converts is not fixed. And an equally likely scenario might have been something like this, where the second shower just kept going and left a detector before pair converting. So in this hypothetical event, you can see that these are now topologically indistinguishable. We have 2 true protons and 2 true photons. So if we reconstruct them well, these are topologically very big background. To be clear, there are many ways the second photon can be lost. It can escape the detector before pair converting. You can have highly overlapping showers, so we reconstruct them as only one. And one of the showers could be very, very low energy, where our reconstruction is a bit lower. We can also have the case that a cosmic ray interferes or is overlapping with the subleading shower. As microboon is on the surface, this can happen. But the key takeaway here is that the neutral current pi zero events outnumber our true single photon events by over 100 to 1, and there are many ways that pi zeros can mimic our signal. So we really do need a measurement of NC pi zeros in microboon to make sure that we're simulating it correctly for our single photon search. So to develop such a selection, we begin with the Pandora pattern recognition framework, as do many analyses in microboon. And from Pandora, we select all events which have 2 reconstructed showers and 1 reconstructed track. So here, this is a cartoon to show we're basically looking for a similar topology to what I've shown you in the event display. On top of this, we're going to add some simple cuts first. 1, a shower conversion distance. So the showers must be at least 1 centimeter away from the proton. This is really to minimize the amount of electrons that get in, because we are trying to be blind to, well, we are blind to the electron side of things. We want to have a quick fiducial volume cut to remove cosmics, and then some kind of minimal energy cuts on the showers to ensure that we have good reconstruction. With a simple pre-selection like this, we have this selection. So this is a busy plot. I'll explain it a little. Here we're looking at the invariant mass that we reconstruct from our 2 showers. And in red here, I have the pi zero components. So the red peaks, as you can see, just around a pi zero mass, and it's split between coherent and non-coherent pi zeros. Coherent being very, very small here, as when you coherently interact with the nucleus, you tend not to, well, you don't stick out any protons from it. So having 1 track, the track is mostly a coincidence track. So it's mostly a non-coherent selection. And at this stage, it's about 25% pure of pi zeros, or neutral current pi zeros. The backgrounds here, as we can see in green, we have a lot of cosmics that tend to pile up at low invariant mass, although there are some true pi zeros in our cosmics, mostly it tends to be bad reconstruction. And we also have a large amount of CC pi zeros, so charged current pi zeros. So this is the case where it is truly a pi zero reconstructing, but there's a long track instead of a short proton, long muon track. So we can repeat this for our 2 gamma 0p, where we have no vertex. This is somewhat more difficult, as reconstructing the angle of the showers when you don't have a track to kind of tag them is a bit more difficult. But the situation remains the same. The backgrounds are also similar. The cosmics are quite large, but the charge current backgrounds here are very small, because it's kind of hard to miss a long muon track. So here, cosmics really are the biggest background. However, we do want to increase the purity. Both these selections are about 25% pure. We do want to increase these, so we've trained 2 tailored BDTs, boosted decision trees, to reject the charge current and the cosmic backgrounds. Now, these BDTs use about 10 various kinematic and calorimetric variables, which I'm not going to go into detail, but I will highlight one of the more important ones, which is the track to EDX. This is the energy deposition per unit length. So in our training data, as you can see, the muons, which is the main backgrounds, travel a long distance while minimally ionizing at about 2 MeV per centimeter, whereas our signal neutral current protons travel quite short distances and are very highly ionizing, stopping in Bragg peaks. We can also look at data, and we can see that we see the same effect where our charge current in our cosmics, which is mainly muon tracks, pile up around at 2 MeV per centimeters, whereas our protons are much broader, stretching out to high DEDX. So the result of this BDT is shown here, which shows our separation between our signal, like pi0 events, as we see in red, and the majority of our backgrounds, which are charge current and cosmics here on the left. And we see good agreement across the range here at microburn. We place a cut, as shown here, to basically optimize our signal efficiency times purity. And we have a very similar version of this for the 2 gamma 0p, but I don't really have time to show that today. Once we place this cut, we come to our final selection for our 2 photon, 1 proton pi0 selection, which is a 63% pure sample. And this, in conjunction with the 2 gamma 0p, represents the largest neutral current pi0 on argon in liquid argon TPC in the world. So we have just over 1,000 neutral current pi0s. If we do a fit to the data, we see that the mean is about just slightly above the pi0 mass with a width of about 44 MeV. And one thing that's quite striking from here is, as I mentioned before, this sample where we demand a proton, and now at the end of the selection where the proton is quite well reconstructed, the fraction of coherent events, NC pi0 coherent events, is basically 0 compared to the non-coherence. This is an almost pure non-coherent component, mostly resonant. The one thing that does pop out from here is that we do see approximately 20% less events in our data than expected. So as the backgrounds of pi0s, as mentioned, is very important for our single photon analysis, we're going to perform an in situ fit to the observed pi0 rate and then correct the Gini prediction in our simulation. However, we are not going to fit in the invariant mass because it's not very sensitive to the coherent and non-coherent changes. Instead, we actually fit in the reconstructed angle of the pi0, which is what I show here. So again, this is the 2 gamma 1p, and this is the equivalent 2 gamma 0p, so no track. And we see that the only place that the coherent pi0 events fall is really in the most forward-going of the 0p. So we fit both the pi0 coherent and non-coherent fractions to our data. And the best fit point, which I show here, which is in very good agreement, favors a 40% enhancement of coherent pion production with about a 20% decrease in non-coherent pion production. Once we've corrected normalization in our simulation, we can then apply this and look at a wide variety of other reconstructed quantities of the pi0s to kind of give us confidence that our pi0s are true pi0s. So the first one I show here is our reconstructed pi0 momentum. And we see that it peaks just below 200 MeV, which we'd expect from the booster neutrino beam at Fermilab. And it has good agreement all the way out to high momentum, where we might be seeing a small drop off, but it's relatively consistent within errors. The primary shower conversion distance shows that although the majority of showers do convert within about 30 centimeters from the vertex, we can reconstruct photon showers as far as 100 centimeters away from the interaction vertex, showing that these truly are photons. So this really gives us confidence that we understand our NC pi0s in our simulation. And then we can use this to constrain the backgrounds for the single photon analysis. So I'll briefly show the effect of this constraint, although please stay for David Cartelli's talk to see more details. We perform a side-by-side fit to what I showed you just now, our 2 gamma selections, to a similar 1 gamma selections, which will contain our delta radiative signal, so this yellow color here. So we fit these side by side, and as you can see from this correlation matrix, these are all highly correlated, the backgrounds in all of these samples. And shown here in the error bars show our full flux cross-sector and detector systematics that we estimate for our signal channels. This is where we expect to see the actual mini-boon low energy excess signal once we unblind the data. And as we can see, the uncertainty here is quite large relative to the signal that we're searching for. Once we have measured our 2 gamma selections, we can constrain these backgrounds and to reduce them proportional to the statistics of pi0 we have obtained. And a representation of this is shown here, which I'm going to slightly flick back and forth between these. So you can see essentially the effective reduction on our systematic uncertainty for our signal channels is about a factor of 2 across most energies, which is has a dramatic effect on the sensitivities that we can achieve. So in conclusion, I've presented here the largest selection of neutral current pi0s in a liquid argon TPC in the world. It provides a strong constraint to the main background to the microburn single photon excess, which was the primary purpose here. This in situ measurement that we performed allows for corrections to default Gini prediction and currently favors about 40% increase in coherent pion production with a slight reduction in non-coherent pion production. So the results I've shown here are for an initial about 6E20 POT, whereas we expect double this for the full microboon data set. And also, once we finalize the single photon analysis, this data itself can be further investigated with a more rigorous cross-section analysis. So for more information on this and other lovely event displays like this, please check out the microboon public note, as mentioned here, which contains all this information. And thank you.
All right, thanks. We actually have time for a quick question, if there is one. Arie, your hand has been up for a while. You should be able to talk now if you have a question.
Yes, thank you. My questions relate to approximately, I need just a number of orders, 1,000 or 10,000. How many Y-zeros microboon have registered? And if you have also answer, how many photons, gammas, microboon have registered? Just number of order. I don't need exact number, just number. Is it hundreds, thousands?
Well, so the final selection, after we've rejected a lot of backgrounds that are not true pi zeros, for our current data set, we have over 1,000 neutral current pi zeros. We have a lot more charged current pi zeros, as Raquel showed in the previous talk. In total, order of magnitude would be, after reconstruction, including reconstruction efficiencies and detector efficiencies, is order, well, very rough, thousands, tens of thousands.
And number of photons? And number of photons?
Well, number of photons from pi zeros, because most pi zeros...
just photons from deltas or other sources, just photons.
Oh, much smaller, a factor of 100 smaller. If it's vast majority of pi zeros in microboon, or showers in microboon, photon showers are truly from pi zeros. So the backgrounds, that's the difficulty of the single photon analysis in microboon, is that we have to reject this factor of 1 to 200 times pi zero backgrounds on top of the very small neutral current delta signal.
200 times.
No. It's roughly, it's between 100 and 200 to 1, depending if you're looking mainly at neutral current pi zeros or CC pi zeros.
All right, thanks, Mark. Thanks, Arie, for the question. We'll have to move on now. Next up is Wouter Van De Pontseele with another channel for microboon. Go ahead and begin when you are ready.
Okay, you can see my screen?
Yes.
Perfect. Okay, so I'll continue with microboon, and I'm going to talk about charge current electron-neutrino interactions in the microboon detector. So the measurement of these electron-neutrino interactions and the kinematics of the lepton are a crucial step towards understanding the nature of the observed excess of low-energy events by the miniboon detector. And this talk will have several aspects. I'll first go into cosmic rejection, the role of electron neutrinos in microboon, electron identification, the event selection, and then I'll show some high-energy sideband results and discuss the near future. So microboon is located in a booster neutrino beam at Fermilab, and we are also fortunate to receive off-axis neutrinos from the NUMI beamline in red. So we are 500 meters away from the booster neutrino beam target. And concerning electron neutrino physics, our first goal is really to identify electron neutrinos in a liquid argon time projection chamber with high statistics. And that's a big chunk of this talk. Furthermore, we can then go on to investigate low energy excess, but also we can measure the intrinsic electron neutrino component in a muon neutrino beam, which is dominated by the muon neutrinos. And we can produce cross-section measurements of these electron neutrinos on liquid argon. To do all of this, we need a lot of prior ingredients, such as detector understanding, which Raquel talked about, and there was also a talk of Ralitza earlier today. We published on signal processing, detector calibration, and several event reconstruction frameworks. To find these electron neutrinos, we also have loads of backgrounds, mainly coming from cosmic activity and muon neutrinos. And all analyses by microboon have 4 main sources of systematic uncertainties coming from the neutrino flux, cross-section modeling, secondary interactions in liquid argon, and other detector effects. Once we find these electron neutrinos, and I'll highlight some of this in my talk, we can go into particle identification, discuss different event topologies, and look at the kinematics of the electron. So as I mentioned before, see a talk by Ralitza earlier today about the general states of the microboon experiment. So there are several steps towards the full unblinding. So electron analysis in microboon are blinded, and this means that we have approximately 5% of our data to prototype or reconstruction and selection on. But we are on the cusp of unblinding a way more extensive 3-year full data set. And this analysis shows some brand new results on a similar sized sideband containing electron neutrinos with a reconstructed energy above 1 GeV, which is far away from our low energy signal box, but is a crucial step towards this full unblinding, which will happen soon. So let's first go into the cosmic rejection a bit. So microboon is a surface detector, which means that our TPC has a cosmic ray rate of around 5 kilohertz cosmic muons. This means that every event has approximately 24 muons in there. And we use off-beam data to model these kind of backgrounds to avoid extra data Monte Carlo discrepancies. So this also means that every neutrino analysis in microboon will start with cosmic rejection tools. The first step in this cosmic rejection is illustrated with this cartoon. So we will first require prompt scintillation light in time with the accelerator trigger. Even if this light is there, we will still have a lot of cosmic charge deposits in the same event. And then we go on with removing geometrically crossing muon tracks and muon stopping in the detector using calorimetry and other geometric information as given in orange. Then there are still several regions of interest with more complicated cosmic charge deposits, and we're going to match the scintillation light here given by the yellow star with TPC activity at charge deposits in both position and the magnitude of the charge and the light to identify a single neutrino candidate in the event. If we do this, we have a neutrino efficiency of 84% and the cosmic rejection at this stage of 99.8%. And at this point, neutrino interactions are really starting to dominate the picture. So electron neutrinos in microboon. As you could take away from the previous talk by Raquel and also by Mark, liquid organ is very complicated and cross-section modeling carries large uncertainties. In the energies of the booster neutrino beam, electron neutrinos come in a variety of final states, such as no vertex activity, protons at the vertex, or also pion production at the vertex, shown by the 3 cartoons on the left. Therefore, this study is going to be an inclusive measurement to be robust against these kind of modeling uncertainties, and it's essential to have an inclusive measurement to support observations that are done in low energy or more exclusive channels, as will be highlighted by the talk by David about low energy access later today. So these plots show the varying contribution of different final state topologies depending on the energy. So at low energies, we see no vertex activities by the blue curve dominating, and at higher energies in green, we see that most events actually even have pions in there. So the next step in the selection is to apply a fiducial volume and identify an electron neutrino candidate. This electron needs then to undergo particle identification because, as Mark mentioned, most showers are actually photons. A liquid organ TPC has the capacity to differentiate between electrons and photons, mainly by looking at the start of the shower. And this is given by the cartoons on the left hand here. So we see simulated event displays of an electron on the top of the page and the photon on the bottom of the page. And an electron will immediately correspond to the ionization loss of a single minimizing particle, while a photon will undergo pair production after a while, so will be detached and will correspond to multiple to 2 minimum ionizing particles, unless in the rarer case of Bremsstrahlung. So on the 2 plots on the bottom right of the page, we see data Monte Carlo comparisons of those 2 discriminating variables. So the first one is ionization loss, where you clearly have the 1 minimum ionizing particle and the 2 minimum ionizing particle peaks. And in orange, you see the electrons are in the first peak and the photons in blue are mainly in the second peak. The plot on the right shows the vertex distance, and here we can see the electrons are mostly at vertex, so very small distances, while the photons spread out over a length of typically 20 centimeters and have a way longer tail, which is shown in blue. So these variables are driving a boost decision tree response, which is given here, which demonstrate that we are capable to effectively differentiate between electron and photons in microboon. So now we identified the electron shower and we tag this as an electron. There are still other particles in the event that we can use to identify which channel we are in and to reject additional backgrounds if there would still have been some muon charge current slipping through. So now we're going to look at all those other tracks in the event. So I'll focus on particle identification, which distinguishes between protons and muons over here. And the differences are based on the beta block function, so the energy losses. Muons are minimizing and have a short Bragg peak towards the end, while protons are heavier and slower, which corresponds to higher energy losses. It's important to take into account a lot of detector anisotropies, which complicate the picture. And therefore, we use a likelihood ratio as our test statistics to differentiate between the two. And this takes into account the angle of the particle compared to the wire planes, and also the distance from the end of the track. We combine the three different wire planes that microboon has by just multiplying the likelihoods. The plot on the left bottom shows you the ionization losses in data for protons and muons. So we can see that the muon has the very short Bragg peak towards the left of the plot, and it generally has lower DEDX values than the proton, which is the red curve, which is a little bit higher. On the right, we can see the output of the likelihood ratio, where the protons in red bump up at the left side, and they have good separation from the muons, which are in brown on the right side of this histogram. So now we did the identification of several objects that occurred in our charge current electron neutrino interaction, and we can move on to the final event selection, which will rely on these previous steps. So the final event selection uses again a boost decision tree, and it's important to state that after the pre-selection, we have a purity of around only 5%, and our main backgrounds are muon neutrino related backgrounds. So on the left bottom plot, all the blue that is popping up there are muon neutrino related backgrounds, and the main one are the pi zeros, which decay into two photon showers and can mimic an electron. So after performing the selection with a boosted neutrino, with a boosted decision tree, we place a cut on the left bottom plot around 0.8. And you can see on the right that there is some green popping up, and this is our electron neutrino signal. So the two plots on the right show the final selection, so the results after the final selection, where we have a signal purity, so electron neutrino charge current of above 50%. And the middle panel shows the electron shower energy, and the right panel shows the track multiplicity at vertex, which demonstrate that we are covering a wide variety of events. So the selection efficiency of the selection outlined here is around 18%, which is given by in function of the true neutrino energy and the green curves below for each of the three topology that I discussed earlier. So it's important to note that we have non-zero efficiency for a wide variety of final states. We can now start looking at the electron kinematics. So here are plots given by the true electron neutrino and the reconstructed electron neutrino energy. And we have a good linearity and the reconstruction resolution of approximately 20%. For the theta angle, which is the angle with respect to the boosted neutrino beam, we have a precision of approximately 3 degrees, and again, very good linearity. Now I'll go into some sideband results. So I said before that we have unblinded electron neutrinos with a reconstructed energy above approximately 1 GeV. And here we can see in green the electron neutrinos, and in blue muon neutrino backgrounds, in gray on the bottom a little bit of cosmic backgrounds. And we can see that we have good agreement with reasonably high statistics in the electron energy and also in the reconstructed angles. So I'll come to my conclusion right now. So this talk aimed to show that we are able to fully automatically reconstruct electron neutrinos in the LRTPC, that we are able to differentiate showers into electrons and photons and tracks into protons and muons. We are able to select charge current electron neutrinos with an efficiency of around 18% and a purity of higher than 50%. And our selection compromises a big set of final state topologies and also covers a wide phase space of electron kinematics. It's important to state that there is a concurrent effort going on with the NUMI beamline, which is completely unblinded and has high statistics. And we are making progress towards measuring the electron neutrino content in the boosted neutrino beam and measuring the electron neutrino cross-section on liquid argon. More information is available in the public note, which is linked on this place. Okay, thank you very much.
Thank you, Wouter. We have time for a quick question. Okay, not seeing any. Whoops, let us move on. And let's see, up next is from T2K, coming Tsui. I'm sure I didn't get that quite right.
Yes.
Go ahead when ready.
Okay. Is the screen sharing working?
Looks good.
Okay, so let me start. Good morning, afternoon, evening, everyone. I'm going to talk about the recent cross-section results from the T2K experiment. So to begin with, T2K is a long baseline accelerated neutrino experiment in Japan designed for accurate oscillation measurement. We have the neutrino beam coming from the J-Power facility in the east coast of Japan. And we have the near detector complex to measure the neutrino flux and interaction parameters. And the far detector supercameo measures the oscillated neutrino spectrum with Wouter-Van technology. So details of the oscillation results can be found in Laura's talk. Now let us focus on our off-axis near detector ND280, where most of our cross-section measurements take place. So inside ND280, we have in total 2 FGDs, fine-grained detectors, which are both neutrino target and the scintillation trackers. While FGD1 is a pure hydrocarbon target, FGD2 contains alternating layers of water to enable water measurement. And savaging the FGDs are free time projection chambers, TPC for short, which provides excellent tracking of charged particles. And with uniform B field from the magnet, we can measure accurate the energy loss and momentum in TPC and enables accurate PID. And at T2K off-axis beam energy, most of our interactions are coming from the charge current quasi-elastic or CCQE interactions for short, with a single lepton and nucleon in the final state. And at a high energy, we start to see resonance productions with extra pion in the final state. And between the quasi-elastic and the resonance peaks, there exists a non-negligible amount of 2-particle 2-hole or 2p2h interactions, where the neutrino can interact with multiple nucleons at the same time. While the experimental signature of 2p2h is similar to CCQE, they have very different reconstructed neutrino energy resolution. So we need to understand the strength of 2p2h for an accurate oscillation measurement. However, neutrino interaction measurement is always not simple because our target is very often not a free nucleon, but a heavy nucleus. That means our initial state nucleon is bound with certain firm momentum and binding energy. And the outgoing hadrons may undergo final state interactions, FSI, where the pions and nucleons can be absorbed or produced additionally. What we can experimentally measure is the final state topology, where all of these nuclear effects are mixed in. In T2K, we usually measure the cross-sections in either the CC0 pi or CC1 pi final state topology, meaning we only observe, we do not observe pion or observe only one single pion. For example, in the CC0 pi topology, it's estimated that only 80% of the true events are from CCQE, and the remaining 20% are from 2p2h or resonance interactions with pion absorption. So if we want to understand the energy resolution or the whole topology things, we need to have some clever ways to decouple such effect. One strategy that's really on point is the joint measurement. For example, by selecting the neutrino interactions at FGD1 and FGD2 at the same time, we can measure simultaneously the carbon and oxygen CC0 pi cross-sections and get the correlations and ratios between them properly. And in this analysis, we have multiple signal samples. That's the pions and proton going into the different subdetectors with different absorptance. And on the right, you can clearly see how the carbon and oxygen interactions can be separated into two FGDs. So here we showed our measured carbon and oxygen cross-section in a low angle forward beam and a high angle beam respectively. On the right is the chi-square agreement compared to 4 state-of-the-art generator models. If we look at the forward angle beams, we can see the data favors the more simple CCQE Fermi gas nuclear models, or LFG in the legends, where these models have a large RPA correction that suppresses cross-sections in the low energy transfer region. The most sophisticated models like spectral function or relativistic mean field doesn't have this correction, and you can see they have much larger chi-square in these regions. On the other hand, if we look at the high angle beams, LFG and actually all other models have underestimated data loss, especially for oxygen. And in these regions, the CCQE component is more affected by the nucleon form factors instead of nuclear models. And CCQE alone cannot explain such large carbon and oxygen difference. So we start to think that we may need to improve the non-QE part instead, which means the current 2P2H and the pion FSI models has to be improved because they are still based on a simple Fermi gas ground state. Next, we look at a similar joint measurements between neutrino and anti-neutrino CC0 pi cross-section, again in FGD1. And this measurement employs a similar method as the previous analysis and actually has broadly similar conclusion. That means for the Fermi gas model, we need some reductions in the forward angles, but some enhancement at high angles. At the same time, this measurement is particularly interesting to 2P2H because the different 2P2H models can predict a very different actual vector component, which can then be translated into neutrino and anti-neutrino cross-section difference. Indeed, if you look at the plots, you can see for the 3 different 2P2H models that was put here, they have some interesting difference between neutrino and anti-neutrino predictions. However, for this measurement, all the models that we compared have a large chi-square per degree of freedom, meaning that no models on the market can describe the whole neutrino and anti-neutrino results well. Okay, this is for our CC0 pi results. Now let us switch the topic to CC1 pi, which is an even more uncharted territory. In the theoretical side, there are much less model development, and sophisticated models like spectral function do not always have their counterparts in the pion channel. And experimentally, there are also less pion cross-section data to compare with. On the right, we showed a CC1 pi cross-sections results from T2K, which measures muon and pion kinematics. Unfortunately, in this phase space, different models only show mostly normalization differences, which are not effective in separating them. So we need a better strategy than just measuring the kinematics. So in view of this, we have recently performed a new cross-section measurement in the CC1 pi channels with at least 1 protons in the final state, and use the muon, pion, and proton tracks to construct 3 different transverse kinematic imbalance or TKI variables for short. The first variable is the double transverse momentum imbalance delta PTT, which is defined as the imbalance between the proton and the pi momentum in the double transverse plane to the neutrino and muon direction. When there's no nuclear effects like an interaction on hydrogen, this quantity is exactly 0. But for a heavy nucleus like carbon, this is no longer 0, and the width of the distribution will depend on the strength of the nuclear effects. The second variable PN is the initial nucleon momentum, where in the impulse approximation picture, we assume the initial nucleon has the momentum Pn, and the remaining nucleus acts as a spectator with an equal and opposite momentum. We can then solve for Pn using simple conservation laws. The third variable delta alpha t is the transverse boosting angle, which is defined as the negative angle between the muon transverse momentum and the sum of the transverse momentum vectors. And this quantity defines whether the hadronic system is accelerated or decelerated by the nuclear effects, mostly in terms of FSI. And in T2K, we perform this measurement in FGD1, which is the hydrocarbon target. And we consider only one single signal sample where all three particles go into the TPC. On the right, we showed the reconstructed TKI distributions with the event breakdown. The overall signal purity is over 60%, and we have 4 CC control samples to constrain the multi-point background. And together with the phase space restriction on the signal particles, we perform a maximum likelihood fit to unfold the cross-section into true variables and normalize it by the flux and the number of targets. Here we showed our measured TKI cross-sections with predictions from 4 different nuclear models. Neut uses the simple Fermi gas models for pion production. For Neutro, we pick up 2 more sophisticated models. One is the Bodek-Ritchie parameterization of RFG, and then other is the effective spectral function. The 4th model, GBoost, uses a local Fermi gas-based nuclear ground state, but with a transport theory that describes all interactions, nuclear correlation, and FSI in a consistent framework. And you can see that as opposed to the C0 pi case, this time the data prefers the more sophisticated nuclear model instead. And the best agreement is as shifted in GBoost. While the sensitivity is a bit diluted by the hydrogen interactions, we can see the 3 variables shows a great potential in constraining the nuclear effects in carbon. In particular, delta PTT and PN are more sensitive to the initial nuclear state, while delta alpha T is more sensitive to FSI. So in future, with more statistics, such measurements would be extremely useful in separating these 2 different nuclear effects components. And okay, this is my last slide. So before I end, let me summarize the coming T2K cross-section program you may see. In the future, we will be having more joint measurements, for example, in the C0 pi and versus CC1 pi data, and also between our on and off axis detectors, which gives us exposure to different neutrino energy. At the same time, we are also having more measurements in the hadronic kinematics, such as the TKI variables or the pion to proton kinematics. And with the coming ND280 upgrade, which is explained by David later, we will have much better capability in the hadronic channels. And finally, we will also measure the neutrino, electron neutrino and neutral current cross-section as well. And with all these programs, we aim to understand neutrino interactions in all aspects and prepare ourselves for the upcoming oscillation charts. So stay tuned and let's measure cross-sections. Thank you.
Thank you, Kaming. We have time for questions. You can use the raise hand feature of Zoom if you'd like to ask a question. Okay, not seeing any hands. Let's continue with the T2K program. Next is the oscillation portion of the program. Laura Montonu, apologies. You can begin whenever you are ready.
Sure. Just a second. Can you see my slides?
Yes, and it is now full screen.
Okay, fantastic. Hi, my name is Laura Montano, and I'm going to give the talk about the neutrino oscillation results from the T2K experiment on behalf of the T2K collaboration. In this talk, I'll first describe briefly what neutrino oscillations are, then go on to describe what the T2K experiment consists of briefly, describe our oscillation analysis strategy, our oscillation parameter measurements, and conclude some future plans and a summary and outlook. So we know that the neutrino mass eigenstates are different from the flavor eigenstates, and that we theorize that they are connected through a mixing matrix, which we call the PMNS matrix. Different types of neutrino experiments measure different angles and different parameters of this mixing matrix. So since T2K is a long baseline neutrino oscillation experiment, we have access to the mixing angle theta 3.2 and the mass difference delta m squared 3.2. So what's keeping long baseline neutrino oscillation physicists up at night is the value of the CP violation phase delta CP, the octant of the theta 2.3 angle, and the mass ordering and the consistency of the whole PMNS framework. So in order to actually measure these parameters, we look at the muon neutrino disappearance and electron neutrino appearance spectra, as you can see here on the plot on the left. The maximum oscillation probability is at 600 MeV for the T2K baseline, which is of 295 kilometers. So we use the off-axis effect to obtain a narrow flux distribution, as you can see on the plot below, to obtain a narrow distribution at 600 MeV and to reduce the electron neutrino contamination in our muon neutrino beam. For the delta CP phase, we inferred from the electron neutrino and anti-electron neutrino appearance asymmetry, and we also have a small dependence on the mass hierarchy of about 10%. The T2K experiment has already been described briefly by Kaming, and I would just like to remind that it's a experiment located in Japan, which produces a muon neutrino beam at the J-Park Accelerator Complex, which uses 30 GeV protons, which it then sends onto a target and uses a series of horns to focus them by to select their charge and flavor, and then it is directed at a 2.5 degrees angle off-axis to the Super K detector on the west coast of Japan. We have two new detectors, but I'm only going to focus on the off-axis one, which is the new detector at 280 meters, or ND280, which has also been described by Kaming, which has two fine-grained scintillating detectors, as you can see here in green, mostly carbon or carbon and oxygen-based, sandwiched between three TPCs, one upstream pi0 detector. It is surrounded by an electromagnetic calorimeter and the UA1 magnet, and it is situated at a 2.5 degree angle off-axis. It is used to constrain the flux and cross-section systematic in our oscillation analysis, and I would like to mention that both of our near detectors are also used for exotic searches and cross-section measurements, as you have seen in Coming to this talk. Our far detector is Super Kamiokande, which is a water-based Cherenkov detector. It is located 1,000 meters under Mount Ikeno on the west coast of Japan. It is filled with 50 kilotons of pure water and has a fiducial mass of 22.5 kilotons. And it uses the Cherenkov ring pattern to distinguish between electrons and muons. So here on the right-hand side, you can see, for instance, what a Cherenkov muon-like ring or an electron-like ring looks like. A muon-like ring has very sharp edges, whereas electrons undergo more scattering, so it has fuzzier edges. Since 2009, we have been stably taking data, and this year we've reached 515 kilowatts of stable operation beam power, and we now have a total of almost 2 and a little more than 1.5 times 10 to the 21 POT in neutrino and anti-neutrino mode, respectively. So in order to get to our oscillation parameters, we perform a fit between the Super Kamiokande data by using our neutrino spectrum prediction at Super Kamiokande. In order to obtain this neutrino spectrum prediction, we combine the Super Kamiokande detector uncertainties with constraints on the flux and cross-section parameters that we obtain with the T2K near detector. In order to obtain these constraints, we fit the near detector prediction to the ND280 data, and the near detector prediction is made up of three main ingredients, which are our flux model, our detector model, and our cross-section model. We have two strategies to obtain these oscillation parameters. The first one is a two-step frequentist fit, which happens first at the near detector and then at the far detector. And we also have a Bayesian fit, which fits both the near detector and the far detector data simultaneously, and they cross-check each other. Regarding our flux uncertainties, we simulate our primary interactions with Fuka, and we then reweight them to Na61 shine data. So previously, we used to use the Na61 shine data that was obtained with a thin graphite target, as you can see on the first plot. This year, we have finally started using the Na61 shine data obtained with a full T2K replica target, which allows us to lower our uncertainties as a function of neutrino energy, as shown on the plot below, from 8%, as shown on the dash with the dashed line, to 5%, shown on the solid line. The samples at ND280 are based on the three dominant scattering processes at the T2K energies. I'm not going to describe them in detail because many speakers have done them before, but we try to define our samples to be enriched in each of these processes using our reconstructed Pi multiplicity. We divide our samples between the FGD1 and FGD2 and neutrino and anti-neutrino beam modes, and we also have a wrong sign sample, which is designed to monitor the neutrino background and anti-neutrino beam mode, which gives us a total of 18 samples to fit. Our cross-section model has moved from a relativistic Fermi gas plus relativistic phase approximation that we used in 2018 to a tuned Ben-Haar spectral function. For the 2p2h uncertainties, we have a new uncertainty on the energy dependence of the cross-section. The removal energy systematic, which is the energy to extract a bound nucleon, now has a much smaller uncertainty due to constraints from electron scattering data. We now have correlated pion final state interaction errors between the near and the far detector, and a much improved multiply and DIS treatment. So when we combine all these things together, we get our near detector fit. And as you can see here, it has a very good flexibility to reproduce well the data, rendering a p-value of 74%. Here is the pre-fit and the post-fit as a function of muon momentum at the near detector. Before the fit, there are no correlations between the flux and the cross-section parameters. However, our near detector fit introduces anti-correlations between the flux and the cross-section parameters, as you can see from this post-fit correlation matrix. This allows us to lower our pre-fit uncertainties from 13% to 4% at the far detector across all 5 samples, which I am now going to describe. The SK samples and data consist of 5 samples, single ring selections, which are based on lepton flavor. In the plots that I'm going to show, the red bands correspond to the systematic uncertainties after the near detector constraint. So for the muon samples, we have 2 muon samples for neutrino and anti-neutrino mode, and they're dominated by CC0 pi events. Whereas for the electron-like samples, we have 2 that are CC0 pi dominated, which are the 1-ring electron for neutrino and anti-neutrino. And we also have 1 sample, which is the 1-ring electron, 1-ring Michel electron, which is enriched in CC1 pi events, and it has larger systematic errors. Now, by looking from the NUI appearance spectra, which you can see here on the right-hand side, we can compare them to the different predictions for different values of the delta CP angle. On the left-hand side, you can see the number of neutrino E-like candidates, the neutrino mode E-like candidates and anti-neutrino mode E-like candidates, compared to the different predictions of the PMNS framework, a theoretical framework, and compared to our data. So this is where our data currently is, and the solid lines here for the different PMNS predictions correspond to normal hierarchy scenarios, and the dashed ones correspond to the inverted hierarchy scenarios, and the different colors correspond to different angles for the theta, different values for the theta 2-3 angle. And in the gray shaded area, you can see our best fit point with its 1 sigma error. Now, before I move on to more quantitative statements, I would just like to show that the contours for in the delta CP sine square theta 1,3, which is the reactor angle phase space, show that our contours for theta 1,3 are fully compatible. So in blue here, you can see the TTP contours, and in red, the PDG 2019 value, and they're fully compatible at better than 1 sigma level with the PDG 2019 value, and the rest of the results in this talk will have this reactor constraint applied. Our delta CP intervals, the one-dimensional ones, show that CP violating values are preferred. Quantitatively, this means that we exclude 35% of all delta CP values at 3 sigma, and that the CP conserving values of 0 and pi are excluded at 90% confidence level. And we also have a small preference for normal hierarchy. The atmospheric sector results show that we have a slight preference for the upper octant, and there are multiple ways in which this could go wrong, and we have thought about that. So we know that our models aren't foolproof, and we wanted to test the robustness by using alternative models, tunes, or educated guesses. So for instance, we would look at using alternative 2p2h models, or different external data, or ND280 data-driven tunes. We performed multiple robustness studies, and the largest impact we saw was a small bias of 1.4 times 10 to the minus 5 on delta M square 32, which we've added as an additional uncertainty. And the effect of including the largest uncertainty from these robustness studies on the delta CP intervals was to move them by 0.073 to the left and 0.080 to the right. So our next steps, JPark will perform a main ring upgrade for a high intensity neutrino beam. We are now operating stably at 515 kilowatts, and the target is to reach 1 megawatt. The near detector upgrade will be happening soon, which, as you will see in Davide's talk right after mine. Super Kamiokande has started loading its water with gadolinium salt, which will help us enhance our neutron detection capabilities. We are working on new and improved selections, and that we are planning to include at both ND280 and Super Kamiokande for the next analysis. And we have signed MOUs with both for the T2K SK atmospherics joint fit and the T2K NOVA joint fit. Combining these different neutrino datasets and energies will help us live degeneracies and reach better sensitivity for both experiments. So in summary, the new results obtained by T2K exclude 35% of delta CP values at a 3 sigma level. We have a slight preference for the upper octant of theta 2,3 and normal hierarchy, and this analysis is the result of many improvements, namely nearly twice as much data as in the previous analysis at the near detector level, 33% more data at the far detector neutrino mode, a new replica target flux tune for many 61 shine data, and huge improvements in the systematic treatment of cross-section uncertainties, and a generally improved fitter framework. We have exciting plans for the future, such as the ND280 upgrade and future joint fits, and thank you very much for your attention. I'm ready to answer your questions.
Thanks, Laura. Yes, we have time for some. If anyone would like to raise their hand. Okay. Well, let's continue with the TDK topics. Next up is Davide Scalaberna with the ND280 upgrade.
Yeah, hello, can you hear me?
Yes.
Okay. Can you see the slides?
Yes, looks good.
Okay, perfect. Yeah, I'm reporting about the status of ND280 upgrade. So yeah, I mean, you already heard about the latest results of T2K experiment, and what I can say is that T2K is planning to extend the data taking to achieve a sensitivity close to 3 sigma, and basically with data taking until 2026. But more statistics is not enough, so we need also to reduce the systematic uncertainty. Right here, you see what was the status of the current ND280 near detector. We have 2 target neutrinos made of plastic scintillator bars, as you can see here in this image, and then everything. Particles produced by neutrino interaction in the plastic, then they are detected in the TPC as well as in the ECAL, and everything is in a 0.2 Tesla magnetic field. So you heard about the status of the current cross-section analysis, and as you heard, there is not yet a model that can actually describe very well all the data. For example, this one is an example of the muon, neutrino, and antineutrino joint analysis. So what we can do is to try to collect more precise data, and so what are the weaknesses of ND280? So the first one is the muon detection efficiency. So here you can see the efficiency as a function of the angle, cosine of the muon angle, and basically the efficiency is pretty high mainly for forward going muons, but then as long as you go to higher angle or backward, then efficiency goes down, but also systematic uncertainty becomes larger, and as well. So here you can see approximately what this region covered by high efficiency correspond for NUI candidates at the far detector. So this becomes what you see here. It means that we need to rely on model extrapolation to different phase regions of the phase space. Also, the proton detection efficiency is not low, so we are about 500 MeV. So these are all things that we will try to improve with this new upgraded version of ND280. So part of the Pi0 detector will be replaced by a tracker. So additional 2 tons of plastic scintillator, which is basically sandwiched between 2 TPC, time projection chamber, one above and below, to measure actually the kinematics of particle exiting the scintillator tracker, and everything is surrounded by a time of flight detector to reduce autoclusial volume background, as well as measuring precisely the direction of the thrust by timing. And again, everything will be in a magnetic field. So this will come together with a beam power increase from 0.5 to 1.3 megawatt. So this is an example of a neutrino interaction in the upgraded ND280. So you have an interaction in the super FGD, which is the scintillator tracker, and then you have a pion, a proton, and a muon. Then you can detect particles in the forward TPC as well as the high angle TPCs, and as well as in ECAL.
So what is the super fine grain detector? So it's a scintillator detector made of polystyrene scintillator. So it is made of about 2 million cubes of 1 cubic centimeter each. And as you can see, basically each one is optically isolated, and it can give it provides 3D out views by 3 wavelength sheeting fiber, and then basically for relatively low multiplicity events like we have in neutrino, then it is something quite close to 3D reconstruction. So yes, this basically allows to have acceptance very high as a function for any angle of the produced particle, but also given the fine granularity, also a quite low momentum threshold for protons, for stopping protons. Yeah, we characterize the detector. So we had several beam tests. What we saw with different prototypes, this one is with is the super FGD prototype with about 10,000 cubes. And what we found is about an average light yield, scintillation light yield of about 41 photoelectrons measured with the silicon PM at about 1 meter wavelength sheeting fiber length. But also this detector is quite fast. So for a channel is sub nanosecond, but then for a cube with 3 fibers, then it's about half nanosecond. So here you can see data comparison with Monte Carlo. So this is the detection of the Bragg peak, and this is an example event display from data. And here you can see the DDX resolution for protons against muons, so that can provide quite good separation with the resolution for muons down to better to 10%. So we had another prototype you can see here in the picture, and this one basically contains all the details of the almost final version of the detector. As you can see, is quite different from the photograph in the previous slide. And this test beam, the goals are the characterization of the detector response for interacting neutrons, but as well as a measurement of the total cross-section. Here you can see an example of how you could see a neutron interaction in the super FGD. So yes, that's about the super FGD detector. The new time projection chambers will have about the similar goal to what we have in the current TPCs. So a good momentum resolution and the accuracy resolution. But we plan to use a new sensor, a new detector. So resistive micromegas. The previous one was without the resistive foil. So why we need that? Because this allows to spread the charge toward more paths, and basically by using the charge sharing, we can get a much better space point resolution. And here you can see we had test beam both at CERN. You can find more details in the backup, and also we publish a paper, as well as in DAISY. Here you can find actually plots from DAISY. This is the space point resolution at about 10 centimeter drift distance, which is almost under 50 micrometers. But then still the DDX resolution is pretty good, better than around 10%, basically, depending on the particle as well. So this means that we can get the same better performance than the current TPC, but with a reduced number of channels. So also the TPC field cage is quite different from what we have now. So here you can find, you can see the current prototype running now at CERN, and it is collecting data. And here you can see an event display showing a muon crossing the TPC. This has about 27 kilovolt at the cathode. Yeah, the last detector is the time of flight, which is a plastic scintillator based one. So this doesn't need a wavelength sheeting fiber to read out the light, but is basically J200 class plastic scintillator. So very long attenuation length and very fast timing. In fact, it can provide a time resolution of about 150 picoseconds. So then it can allow to measure the track direction and also to reject all the out-of-crucial volume. So what do we expect to achieve with this upgraded detector? So here you can see in purple, you see the detection efficiency for muons. That's only for muons with the current part of ND280. So with the fine grain detector, if we have interaction in super FGD with muons exiting the super FGD, so detected by TPC, you can see that here the efficiency is pretty high. But then also if you include muons stopping in the super FGD, then the efficiency becomes almost flat above 17, close to 80% for high angles. Also, the mass is about this about twice, so we expect to collect much more statistics. The fine granularity of the scintillator detector also allows to do more precise studies of short, low energy protons as well. So, for instance, this one is an analysis performed using what we call the singleton as variable you heard about in a few talks already today. And if we combine many variables built on the transfer on the transfer plane, basically, we can distinguish, at least infer, the different nuclear effect. For example, here you can see the tail dominated by CCQE. If we look to a different delta alpha T angle, and here is mainly dominated by 2p2h. So we did some sensitivity studies. So first, we expect to be able to distinguish, to some extent, nuclear effect from flux normalization, but also to constrain the 2p2h normalization down to 2-3%, so by a factor of almost 2, if I remember correctly, and the binding energy down to 1 MeV with a T2K high statistic. Yeah, I mentioned that we are collecting data, neutron data. We are exposing the prototype to Neutron. So we believe that we can do new analysis with Neutron. So because scintillator, plastic scintillator is a good material for achieving high efficiency. So this one is the detection efficiency, the function of the kinetic energy of the neutron versus the angle of the neutron, of course. The more mass material the neutron sees, the higher is the efficiency. And here you can see the neutron multiplicity on the y-axis. This is the statistical uncertainty, basically. So on the neutron multiplicity as a function of the energy. Also, thanks to the good timing and the 3D granularity, we will try for the first time to measure the energy of neutrons produced by neutrino interactions with the time of flight technique. And here you can see some curves that shows the energy resolution as a function of the true neutron kinetic energy. And that may allow also to have a sort of separation between hydrogen and carbon by looking to the delta PT, to the transfer missing momentum. So you can find more details here with to infer measurement in hydrogen neutrino hydrogen interaction, but as well as anti-neutrino flux. So conclusions. So T2K, you saw from previous talks, is continuing to produce high quality data, and the plan is to extend the data taking until 2026. To improve actually the search for CP violation, and about 3 sigma significance for rejecting CP conservation if actually CP is violated needs a better understanding of the neutrino interaction model. So we will have a almost continuous data taking until hyperchemical starts with an increase of the beam power, but as well this will come together with the upgrade of the ND280, which whose installation will be in summer 22 in J Park, and then it will be ready to start collecting data in fall 22, of course, given still some uncertainty to situation of COVID-19. Thank you.
Thank you. We have time for questions. Yeah, go ahead, David Caratelli.
Hi, yeah, thanks, Davide. This is David. I have a question on your proton efficiency on slide 7.
Yeah.
Oh, thank you. So I think I understand why the threshold moves down, but I don't understand quite well why the efficiency also goes up overall with the new detector.
Yeah, because so this one is the FGD, so is with is this type of detector. So overall the efficiency it depends also on the angle, right? So I mean, particularly this plot was done by requiring at least 3 hits in XYZ, right? So this detector requires longer tracks, but also overall this gives also a reduction of the total efficiency. And in fact, if you yes, in this case, any hit, 3 hits in 3 different queues is basically one track of 3 hits. This is the difference between the two.
Thanks.
Any other questions? All right, thanks a lot, Davide.
Thank you.
And next is Michael Baird with results from NOVA.
Okay, can you hear me?
Yes, I hear you, and your slides are in full screen.
Okay, great. So first, thank you, Ryan. Thank you to the organizers for inviting me here to give this presentation today. And special thanks to everyone who worked very hard to transition this from a in-person conference to a virtual one at the last minute. So, oh, hang on, I'm having trouble advancing. Let's see, there we go. I think I'll have to click this button here. So let me start with a little bit about neutrino physics. We just heard a few excellent talks from our colleagues at Decay, so hopefully this section could be quick. So there are many unanswered questions in neutrino physics today. We know that the neutrino mixing can be described by the PM&S mixing matrix, which involves 3 real rotation angles and a CP violating phase factor. And in addition to that, you need 2 squared mass splittings. And despite the fact that we've been studying neutrinos for decades, there are many unanswered questions. And let me list a few that are relevant to the results I'm going to show you today. So first, there's this question of the hierarchy. This is the question of whether or not the third mass state is greater than or less than the first 2. Then there's the question of whether or not neutrinos exhibit CP violation. Experiments have begun to make measurements of this CP violating phase factor. We're looking to refine that measurement. This is potentially related to the question of the matter-antimatter asymmetry problem in the universe. And then there's the question of the underlying texture of the PM&S mixing matrix. Specifically, as you heard in the T-decay talk, what is the octant of the mixing angle theta 2,3? We know that this angle is very close to being maximal, but we don't yet know if it is slightly less than 45 degrees or slightly greater than 45 degrees. And that determines the extent to which the flavors mix together in the third mass state. So NOVA attempts to try to measure nu mu survival probability and nu E appearance probability from a primarily nu mu and anti-nu mu beam in order to try to answer these 3 questions. The nu mu survival probability depends upon theta 2,3, delta m squared 3,2, and the neutrino energy. And to give you a preview of what we might see at the end, if we didn't have oscillations, then we would expect to see this dashed line as an example of what the energy spectrum would look like for nu mu events that are far detector. But because oscillations do occur, we see this solid line, something more like this solid line down here. And so by identifying nu mu events and by measuring their energies, we can reconstruct this spectra, and then we can fit for theta 2,3 and delta m squared 3,2. The nu E appearance probability is a significantly richer expression. It gives us access to all 3 of those questions that I stated at the beginning, the hierarchy, delta CP, and the octant of theta 2,3. And so we like to try to visualize this in what we call the bi event or the bi probability plot. So we plot on the bottom axis here the total number of appeared electron neutrino events, and on the vertical axis is the total number of appeared anti-electron neutrino events. And so you see these 4 ellipses over here. And these 4 ellipses, excuse me, represent the 4 combinations of the hierarchy, the normal hierarchy in blue, the inverted in red, and the octant, upper octant on the upper 2, and then the lower octant down here. And then the different points on each of these ellipses represent the possible spread of values of delta CP from 0 to 2 pi. So you can see that different combinations of these 3 factors can produce asymmetries in the appeared nu E versus appeared anti-nu E rates. And so our job then is to try to do a simultaneous fit to the nu mu, nu E, anti-nu mu, and anti-nu E spectra as measured at our FAR detector. And that's what gives us a handle on these 3 questions I posed at the beginning. So let me tell you a little bit about how we do that. So NOVA is an experiment that uses the NUMI beam. NUMI stands for neutrinos at the main injector, which is provided to us by Fermilab. This is the main injector ring over here. They provide us a 10 microsecond beam pulse, roughly every 1.5 seconds. We have two magnetic focusing horns that can charge select either pi plus or pi minus to give us either a 95% pure muon neutrino beam or a 93% pure anti-muon neutrino beam. And the beam has been running at greater than 700 kilowatts since about 2017. Fermilab is currently working on upgrades towards PIP2 that should reach in excess of 900 kilowatts. The talk that I'm showing you here today, if you've read our paper from last year, this talk shows 50% more neutrino beam mode data over those results from last year. So our detectors, we have designed to be as close to being functionally identical as possible. You can see them depicted down here. We have two, a near detector very close to the beam and a far detector far away from the beam, as depicted with a cartoon person down here. The near detector is about 300 tons. It sits a kilometer from the beam and it's 105 meters underground. The far detector is 14 kilotons. It's 810 kilometers from the beam source and it sits on the surface. And both detectors are made out of extruded PVC cells. You can see an example of one over here. These cells are about 4 centimeters by 6 centimeters wide. They are filled with mineral oil as a scintillator, and then we have wavelength shifting fibers draped down the length of them that collect the light and send it up to an avalanche photodiode for collection to go to the DAC. So this results in having two detectors that are basically pixelated tracking calorimeters. So these are example events from our near detector data. So this is a new mu-CC candidate event. You see your hadronic recoil system here and a nice long muon track. And then this is a candidate nu-E event. So you see again a hadronic system and an electron shower instead of a muon track. And then here's a neutral current candidate event. Again, there's some kind of hadronic system, but instead of a lepton, in this case, you might have something like a pi 0, which has decayed into 2 photons. So the job of our analysis then is going to be to try to identify neutrinos and separate them by flavor, specifically for the results I'm showing you today, muon neutrino and electron neutrino events, and then reconstruct their energies such that we can fit to the final spectra. So let me tell you a little bit how we do that. So I'll tell you about event selection first. So if you've ever seen a NOVA talk, of course, you've heard that we use this thing which we call CVN. It's a convolutional neural network, which we call the convolutional visual network. It yields for us an increase in exposure of about 30% over traditional PIDs. We were the first particle physics experiment to use this in analysis. Here's the paper if you want to follow the link to read about how it works. I won't tell you all the details about how it works today. One of the things I'm excited to tell you about are some of the improvements that we've managed to get through for this analysis. Not only have we retrained it, but we've implemented a variety of technical improvements that have overall led to a factor of greater than 10 boost in speed for both training and evaluation. This has opened the door for us now to do a lot of investigative studies into our PIDs, retraining multiple versions, trying them against each other. We're pretty excited to explore that landscape in the future. So once we have identified new mu-CC and new ECC events, it turns out for the new mu events that our sensitivity depends primarily on the shape of the energy spectra. So to enhance that, we separate these events into 4 quantiles based on hadronic energy fraction, which is essentially a proxy for energy resolution. And this has the benefit that most of the background events end up in the 4th quantile, which you can see over here, the quantile that has the worst energy resolution. For the new E events, it turns out that the sensitivity depends primarily on our ability to separate the signal events from the background. So we divide them into 2 categories, the low PID events and the high PID events, which helps isolate a much higher purity sample. We still can get some sensitivity out of those, which is why we include them. And then we have this 3rd sample over here that we call for the peripheral sample. These are events that are not contained, but pass a much tighter selection of cuts on our PIDs. And we do not attempt to bin these events in energy when we reconstruct them, we just count them. So let me tell you a little bit about our extrapolation. So we've used roughly the same extrapolation technique that we've used in previous analyses. This is a technique by which we modify our far detector prediction based on any differences in the near detector data in Monte Carlo. This has the benefit that it significantly reduces any correlated uncertainties between the 2 detectors, specifically cross-section and flux. But our near detector containment does limit the range of accepted lepton angles more so than in the far detector, and that's depicted in this cartoon over here. So in this analysis, this is new, we've attempted to mitigate this by extrapolating in bins of transverse lepton momentum. You can see an example of the distribution of transverse lepton momentum for near detector events in red versus the far detector events in blue. And we have the data here in black. You can see that the data between the near detector data and Monte Carlo does match reasonably well, but any differences here will get extrapolated to the far detector. So we split the near detector sample into 3 bins of transverse momentum, and we extrapolate each separately to the far detector. The PT bins are resummed before we fit, so that they are only used as part of the extrapolation and not used as part of the fitting. And this has the overall effect that it rebalances the kinematics to better match between the detectors. So in terms of our systematics, if you look at just the nominal extrapolation that's depicted here in red, and then adding this PT binning extrapolation is what's depicted here in orange, you can see that for almost all of the systematics, they come down, they get a little bit smaller. The one that gets a little bit larger is lepton reconstruction, which I think is understandable given the way this technique works. But we believe that we understand lepton reconstruction very well, so this is not something that makes us uncomfortable. This also, we believe, increases the analysis robustness against unknown unknowns. But most importantly, you can see that neutrino cross-section systematics come down by about 30%, thereby reducing the total systematic uncertainties by 5 to 10%. Okay, in my remaining couple minutes, let me show you some of our results. So I always like to start with some event displays from our far detector data. So here's a new MU-CC candidate event taken in March earlier this year. And here is a new ECC candidate event also taken earlier this year on February 14th. So here's all the data together then. This is the new mu data only. On the left, we have the neutrino beam mode data, and on the right, we have the anti-neutrino beam mode data. So you see that we observed 211 events on a prediction of 222 with an estimated background of about 8. And for the anti-neutrino beam data, we observed 105 on a prediction of 105 with an estimated background of about 2. For the new E events, we observed 82 on a prediction of about 86 with about 27 backgrounds. And on the anti-neutrino side, we observed 33 on a total prediction of about 33 with a total number of backgrounds of about 14. So when we apply our fits, this is our contour in sine squared theta 2, 3, delta m squared 3, 2 space. So this is our contour in black with our best fit over here. You can see this gives us a preference for the normal hierarchy. But you can also see that we have a nice competitive, consistent result with other experiments out there. Now the caveat for this plot, this is the plot that we showed a few weeks ago at Neutrino 2020. Several of these experiments have shown updated results then, but we don't have the updated contours yet. So these are their old, these are not their most recent results. But we're working with those experiments to improve this plot now. Then on the sine squared theta 2, 3 delta CP space, we get a best fit for delta CP of about 0.83 pi, which puts us about here. This is the normal hierarchy up here, inverted down here. And so you can see that we also have a slight preference for the normal hierarchy. Now let me return to this by event plot. So when we put our events on this plot, we end up somewhere here, right about in the middle of all 4 of these ellipses. So we see no strong asymmetry in the new E bar appearance rates. And we disfavor hierarchy delta CP combinations that would produce any such asymmetry. Specifically, we can say that we exclude this region up here at about 3 sigma and this region down here at about 2 sigma. And we have a slight preference for both the normal hierarchy and the upper octant, as I already mentioned. So those are our results. We've performed a joint analysis combining new mu bar disappearance with new E bar appearance results. We're using roughly half of what we expect to be our final data set. We have a preference for the normal hierarchy and the non-maximal mixing in the upper octant, both at about 1 sigma. And we exclude these regions of the asymmetry between new E and new E bar appearance space at around 3 sigma and around 2 sigma. As was mentioned a couple of talks ago, we're also looking forward to continuing our work with T-decay toward the joint analysis. We have an exciting future on the horizon, including both more data for this analysis and more analyses from NOVA's broad physics program, including input from our test beam program, which you'll see in the next talk. So thank you very much.
Thank you, Michael. We have time for questions. Go ahead, Mark.
Hi, Michael. Thanks for a very nice talk. I know that NOVA produces Feldman-Cousins critical chi-squareds for all of their contours. I was wondering if you could tell me how big of an effect this is, particularly for the disappearance parameters.
Oh, that's a good question. Let's see. So as I recall, if you look at these contours before Feldman-Cousins corrections and afterwards, they don't change by very much. So.
Okay, yeah, thank you.
Sure.
Certainly at T2K, we've noticed we do this for our appearance contours, and we see some fairly significant effects there, but I haven't ever seen it for disappearance.
Right.
Any additional questions? We have remarkably recovered some time through the last few talks. So this is excellent for interaction. All right, thanks a lot, Michael. Yep. And what is this? There's something in chat. I'm not sure. It just says hi. Okay, let's move on. Next is Mike Wallbank on the NOVA test beam program. Go ahead, Mike, whenever you're ready.
Okay, thank you very much. I assume you can see and hear me.
Looks good.
Great, thank you. Okay, so yes, thank you very much, and thank you for the opportunity for me to tell you all about the NOVA test beam program. So you've just heard a very nice overview of the NOVA experiment from Michael, so I won't go into too much detail. I'll just remind you that we're a long baseline neutrino oscillation experiment based at Fermilab with a far detector 810 kilometers from the beam source in northern Minnesota. And here you can see some very nice pictures of our two neutrino detectors. And you've also seen some of our recent exciting results. Michael's just given you a very nice overview of the recent analysis of 3-flavor neutrino oscillations. In addition to this, NOVA has a rich physics program using our capable detectors, including making measurements of neutrino cross-sections at our near detector, searching for sterile neutrinos and other non-standard oscillations, and other exotic models and more. So again, Michael's described how we perform our oscillation analyses. So we typically measure the energy spectra of various components, such as I'm showing here the oscillated muon neutrino charge current events that we see in our far detector, and then use each of these spectra to fit to oscillation models so we can make measurements of the parameters which govern the oscillations. So you can see on this plot the systematic uncertainty in the purple band, which is present in this analysis. And beneath, I've shown the breakdown of all the systematic uncertainties for this most recent analysis. And for comparison, the statistical uncertainty for the 2020 analysis is shown in red. You can see it's becoming comparable to the systematic uncertainty. And as Michael mentioned, NOVA has only collected half the data we intend to. So obviously, as we collect more data, the systematics will become more and more limiting, and as this red band shrinks. So you can see currently, for this analysis, we are dominated by our understanding of the detector calibration, with additional uncertainties in reconstructing the lepton and the energy reconstruction of the detectors, and our understanding of the detector response. So we can address some of these largest uncertainties that are present directly using a test beam experiment, where we would use a smaller version or just a version of a NOVA detector in a beam of well understood particles, so we can directly observe how it responds and behaves to particles that we understand well. So using such an experiment, we are validating and searching for improvements in our calibration procedures, improving our understanding of the NOVA detector response, and also collecting a library of single particles for use in improving the simulation of our NOVA detectors and the events in them, and making more complete reconstruction tools. So this is what the NOVA test beam program aims to do. We have a scaled down version of a NOVA detector. This is identical in technology to the near and far detectors, as Michael described. It's just around an order of magnitude smaller than our near detector. And this sits in a beam of charged particles consisting of protons, pions, muons, electrons, and kaons in roughly the 1 to 2 GeV momentum range. And this is most relevant for NOVA, since the neutrino flux that we sample at our two neutrino detectors, at our near and far detector, peaks at around 2 GeV. So charged particles around this momentum are most relevant for understanding the particles we see in our other detectors. Both the detector and also a brand new tertiary beamline that you can see at the bottom here have been constructed and deployed at the Fermilab test beam facility, starting somewhere around a couple of years ago in 2018 through to early last year. We collected data before the summer shutdown in 2019 for a couple of months for commissioning, and then we resumed data taking at the end of last year through to earlier this year. So NOVA test beam uses the M-center beamline, which is one of the external beams provided by Fermilab's accelerator complex. This is the same beam that was previously used by Lariat, and we're located in an area slightly downstream of where Lariat was located. So this beam is derived from main injector protons, which are accelerated up to 120 GeV and then extracted in a continuous 4.2 second spill once a minute. These are the same protons that we use to make the neutrinos in the NUMI beam, which we analyze with our other NOVA detectors. And in our case, we use it to create a tertiary beamline by first impinging these protons onto a target around 120 meters upstream of the NOVA detector to create a secondary beam of slightly lower momenta, mostly protons and pions. Typically, we use a tune of around 64 GeV. And then we use a second target to impinge the secondary beam particles onto to create a tertiary beam. And this is around 14 meters upstream of the NOVA detector and produces the particles of interest for the NOVA test beam experiment. So I mentioned we have a suite of beamline detectors, which we use to characterize and analyze the tertiary beam particles before they interact in the NOVA detector. So here you can just see a schematic of the beam detectors that we have in place. So these provide particle identification and also a precise measurement of the momentum of the particles, so that we know what type of particles are interacting in the NOVA detector. And they also are used to provide a trigger for the types of particles of interest and initiate a readout of the beam detectors, and also tagging the particles as they enter the NOVA detector. So here's a nice panoramic view of our experimental setup out at the test beam facility. Here, beam is moving from right to left. So the target is to the far right of this plot, just downstream of that wall. And you can see our NOVA detector on the far left. And so each of these components in the beamline are shown here, and I'll give you a little bit more detail on each of them now. So we have an analyzer magnet, which is used to select the charge of the tertiary beam particles of interest, and also the momentum that we're interested in by setting the field such that particles of the desired momenta are deflected via the correct amount. The field is capable of going up to 1.8 Tesla, which will give us, which would focus particles at around 2 GeV. We have a time of flight system with an upstream arm and a downstream arm separated by around 13.2 meters. This is used to provide identification of heavier particles, which would traverse the beamline slower than and take longer than lighter particles. So in our case, this is protons and also kaons. We have tracking through the beamline provided by 4 Y chambers. 2 are upstream of the magnet and 2 are downstream of the magnet. So we use these to provide a precise reconstruction of the momentum via the deflection through the known field. And additionally, for particle identification, we have a threshold shrink-off counter just upstream of the NOVA detector, and this contains carbon dioxide at 1 atmosphere. In our experimental conditions, we only expect shrink-off radiation to be emitted from electrons in these conditions. So this is used to tag electrons in the tertiary beam before they enter the NOVA detector. So Michael's already shown you this cartoon and giving you an overview of how the NOVA detectors work. I'll remind you again that the test beam is identical, just a little bit smaller, as you can see from this annotated adapted figure. So our detectors are constructed from planes of cells, which are oriented alternately vertically and horizontally in the direction perpendicular to the beam to allow 3D tracking. The cells are filled with an oil-based liquid scintillator, instrumented with wavelength shifting fibers, and the scintillation light is read out at the end by photodiodes. The front-end electronics, which are used on the near detector and the far detector, are slightly different. So the test beam detector is instrumented with both types, so we can perform characterization of both of our neutrino detectors using the test beam program. So I've shown you some preliminary results here. So everything on this slide is just from our beam detectors. So this shows you the power of our beamline for identifying particles and for characterizing the beam. The data which are shown on this slide were taken earlier this year between January and March, and with two different tunes of the tertiary beamline, one focusing particles at around 1 GeV, and then we also collected a little bit of data focusing particles at around 500 MeV. So you can see from this plot on the bottom right, the reconstructed momentum, which we get from our wire chambers and magnet. So you can see very clearly the large amount of data which we collected at our primary tune at 1 GeV, and then also a smaller amount at half that. This is fully automated reconstruction, and it looks very reasonable. So this is very good. Also on the bottom, you can see the reconstructed time of flight that we get from our time of flight detectors, showing the very nice separation between our faster particles, which are the lighter species, such as electrons, muons, and pions. You can see a small amount of kaons, and then a nice distribution of protons as well, which move significantly slower. And when you look at these against each other, as you can see at the top, you can see the very strong identification capabilities of our beamline to provide the characterization of the particles and the different concentrations of particle species on this plot. Protons here, nice distribution of kaons, and then the faster particles at the bottom. And I'll remind you again that you can't see from this plot, but we additionally have the threshold Cherenkov, which is used to tag electrons. So we can we can separate out any electrons which are in this bottom distribution from that are traveling in the beam. On my last couple of slides, I've just got a couple of event displays to show what these events look like in our NOVA detector. So this is a proton candidate. You can see the particle properties, which are reconstructed using our beamline detectors, and where this sits on the PID plot. So you can see this is very characteristic of a proton that we expect to see traversing our beamline. And on the right, this is the matched event from our NOVA detector. So this event display is very similar to what to the ones that Michael showed, just obviously quite a bit smaller since our detector scaled down. You're looking at two orthogonal views of the detector, one from the top, one from the side. Beam is going from left to right, and each pixel represents the scintillation light collected on a certain cell, with the color scale representing the charge. So again, this is very consistent with a proton-like particle, which appeared to stop sort of halfway through the detector. And on this slide, I have an example electron candidate. Again, you can see the properties of the particle, which we measured from the beamline, which makes this very consistent with a lighter particle. And in this case, we did detect a Cherenkov radiation from our Cherenkov counter. So this heavily implies that this particle was indeed an electron. And as you can see through its interactions in the NOVA detector, you can see the sort of the fuzzier showering nature of the electromagnetic interactions as the electron interacts with the NOVA detector. Okay, so just to summarize, we have deployed a third NOVA detector at Fermilab and constructed a brand new tertiary beamline at the test beam facility for use in the NOVA test beam program. So far, we've collected around 6 months of data from sort of around this time last year to earlier this year, corresponding to some initial commissioning and then some initial data collecting. We are nearing completion of the full calibration of the full detector, which we do using COSMICS in a very similar technique to the near and the far detector. And then following this, we'll begin the process of analyzing the data we collected with a view to improving our understanding of how a NOVA detector responds to well understood particles, and then incorporating any improvements into the calibration and reconstruction chains, and eventually the NOVA analyses. During this current shutdown that we're in, we are working hard to optimize our running conditions by using the commissioning data we've already collected and simulations. And then we expect to operate further beginning when beam returns, which we're expecting later on this year, through to summer of next year. And thank you very much. I'll leave you with some pictures of everyone working very hard on the NOVA test beam experiment. Thank you.
Thanks a lot, Mike. We have time for a few questions. Okay, thanks again, Mike. And let's move to some short baseline talks, starting with Alexei Konovalov with Coherent.
Yeah, hello, let me share the screen. Please indicate if you can see the slides and hear me well.
All looks good.
Okay, so hello, dear colleagues. My name is Alexei Konovalov from ICHEP, Moscow, and I'm happy to present here at ICHEP on behalf of the Coherent experiment. The Coherent collaboration includes 21 institutions from 4 countries, USA, Russia, Canada, and South Korea, and is a part of the worldwide effort to study the effect of coherent elastic neutrino-nucleus scattering. So, to which I'd refer further in my presentation as to sevenths. So this effect was predicted in 1974. It's electroweak neutral current process in which neutrino scatters off the nucleus. If the energy of the neutrino is low enough, below 50 MeV, let's say, then the individual neutrino-nucleon scattering amplitudes interfere, given the enhancement to the total cross-section. And if we are looking at the standard model expression for the coherent scattering, we may notice that the cross-section is proportional to the nuclear form factor, so the details of the nuclear structure, but effectively it's proportional to the number of neutrons squared. So that makes the coherent neutrino scattering the dominant channel of interaction of neutrino with matters, especially for the heavy nuclei. And on the plot on the right side, you may see that for cesium and iodine nuclei, for example, the coherent neutrino scattering cross-section is 2 orders of magnitude larger than the competing process of the charge current and neutrino electron scattering. The payback for such a large cross-section is a small small recoil energy which is transferred to the nucleus. So just to give you the scale for the characteristic energies of the neutrinos at reactor, it's the maximum recoil energy is of about 1 keV scale, and for the pion decay at rest sources, it's of about several keV scale depending on the exact material. Coherent collaboration utilizes the SNS facility, which is in Oak Ridge National Lab in US, where the bunches of 1 GeV protons are being dumped on the mercury target with 60 Hertz frequency, providing, and also releasing the 1.4 megawatt of energy, providing us with total neutrino flux, which is quite large for this kind of facility. So what happens is that the pions are being born in the proton interactions with mercury, and they decay in rest, as well as the muon, which is being born in such a process. And this decay chain at rest gives us 3 flavors of the neutrinos, nu mu, nu e, and anti-nu mu, with the energies below 50 MeV, which suits quite well for the 7th study needs. And also they are concentrated within several microseconds after the beam spill, which gives us, on one hand, additional observable arrival time, and on the other, allows us to suppress the steady state backgrounds quite a lot. The coherent detectors are hosted by the target building, SNS target building basement, which is now dubbed as the neutrino alley, and we have about 20 meters of construction materials with no voids in the direction of the target, and also about 8 meters of water equivalent vertical overburden, which gives us the suppression of the environmental backgrounds and also again, we have the beam timing allowing to suppress the backgrounds even more. So multiple detectors are located there, and we have the different technologies and the materials like argon, sodium, iodine, germanium, cesium. These detectors complement each other in search for the rich physics, which is accessible when you are looking at the seventh-like processes, including the non-standard neutrino interactions, some sensitivity to weak mixing angle, neutrino magnetic moment for muon neutrinos, the details of the nuclear structure from the sensitivity to nuclear form factor, and also inelastic neutrino interactions with materials of the detectors. The first observation of this process, coherent neutrino scattering, was performed in 2017 by the collaboration using 14.5 kilogram of cesium iodine detector. We had a nice 6.7 significance signal, both in from the combined feed of the energy depositions and from the arrival time. And that observation had a quite big impact on the non-standard neutrino interaction and properties, especially for the neutral current ones related to the neutral current, and also for some observables in the nuclear structure physics. I mean, for example, the neutron skin radius of the corresponding nuclei. So in this talk, I'd like to tell a bit more about the SENS-10 liquid argon detector, which was built in Fermilab and moved to SNS in late 2016, where it was upgraded in order to increase the light yield. And it's that 24 kilograms liquid argon single phase detector with the scintillation light providing us with 4.5 photoelectrons per keV of deposited energy, and with the threshold, low energy threshold of about 20 keV of nuclear recoil equivalent. So this kind of detectors also provide us with the pulse shape discrimination opportunity, which allows us to discriminate the electron recoils from beta and gamma's interaction from the nuclear recoils characteristic for the seventh interactions. So this winter, the result was published from this detector. So we have nice spectra in the combined space of the variables as arrival time, the reconstructed energy depositions, and also pulse shape parameter with which are presented in this slide with the steady state background subtracted, and the steady state background was formed from the beam off window. And the three-dimensional distribution was fit to the sum of probability density functions for the beam-related neutrons contribution and from coherent neutrino scattering, and the results of the fit conclude that we observe, we detect the seventh contribution with more than 3 sigma significance. These are the results of the two independent blind analysis, and the results of this analysis agree with each other and with standard model prediction. So if we are speaking about this result in terms of the cross-section, you may see the plots at the bottom of the slide. Again, the results of two groups coincide with each other and coincide with the prediction of the standard model within the current uncertainty, which is currently guided by the statistics. So I'd refer to the publications at ArXiv and to liquid argon data release for the fitting for the further information. We expect about 5 sigma significance by the end of this year for this liquid argon detector. The implementation of this result is that we are first to confirm the n-squared dependence, which is inherited from the essence of the process, from the interference. For the coherent neutrino scattering, you may see the results from argon and from cesium iodine detector overlaid on the expected cross-section with the correction by the nuclear form factor. And another thing is that we have some sensitivity to to the non-standard interaction parameters, something like, and what is presented here is the assuming vector current-like non-standard interaction couplings of electron neutrinos to U and D quarks, and something like this was described today in the session by Alexander Valencia. So this is the combined exclusion limits for non-standard interactions, and let's move on with the status of the cesium iodine detector. So the detector stopped data taking last summer, and currently we have 2 times more statistics than we had by the time of 2017 result. So the main obstacle on the new result is that there is a quite large systematic uncertainty on the quenching factor, so-called quenching factor, which is shown in the gray band as of the state of 2017 in this plot. And numerous efforts were conducted in order to clarify the situation here. So on the coherent side, there was an analysis, cross-check, and reanalysis of 2017 data. There was a new data with a tagged recoil and also new endpoint measurement, which provided the systematic checks for our results. There was also the activities on the side by Professor Juan Calar from University of Chicago. The current state in the plot on the right, and you may see that the scatter of the quenching factor values in the region of interest, again marked with gray, is still quite large, but the behavior of the points of the recent measurements is pretty the same, giving us hope that the global fit would result in the smaller uncertainty and allowing us to move forward for the cesium iodine full dataset result, which is planned to be presented together with the finalized quenching factor at one of the Magnificent 7 seminars on September 18th, so stay tuned for this result. The other detector subsystems which are hosted or are to be deployed in the Neutrino Alley is the naive, the segmented sodium iodine crystal array, 200 kilograms already deployed, 3 tons to be deployed in 2020, which should provide us with 3 sigma significance per year of exposure. And also these detectors are sensitive to the inelastic channels of neutrino interaction with the nuclei, with the iodine in this case. So the germanium detectors, we have ordered 8 detector units with total mass of about 16 kilograms, very low energy threshold, and we expect the characterization and deployment in very soon future for these detectors, which should provide us with about 500 7th events per year. The other detectors, which are NUPs, the liquid scintillator cells surrounded by shielding made either from lead, iron, or copper, and looking for the inelastic processes with the neutrons in the final state. So this kind of interactions can be a background to the 7th search in coherent-like experiments, and also are interesting per se for the Halo experiment looking for supernova neutrinos. Mars detector is looking to characterize the neutron backgrounds in the neutrino alley. So the future initiative of Coherent aimed to the precision measurement of coherent scattering, and the first step is the precise flux normalization, which is currently known only to the 10% uncertainty, known with the 10% uncertainty, and that is planned to do with the heavy water Cherenkov detector, which with a mass of about 700 kilograms heavy water, which can provide us in 2 years about 4% statistical precision, allowing us to move forward with the more massive detectors like liquid argon detector with 700 kilograms of mass, which should provide us with about 3,000 7th a year per year, and also with some rate of the inelastic interactions on the argon, which may be of interest for Dune, as far as I understand. So the future of the neutrinos at SNS is quite bright. There are upgrades of the power of the facility, and also the second target station is to be built, which can provide the hosting for much larger detectors for coherent in future. Another interesting topic which we have access to is the accelerator-produced dark matter. So some models in which, let's say, dark mediators coupled to either to vector bosons or to the only to baryons can be tested with the detector currently deployed in the neutrino alley, and for this kind of experiments where this vector portal dark portal meson is dark portal boson is decaying into the dark matter-like particles, both the seventh process and beam-related neutrons are the background, and they might be constrained by analyzing of the sidebands, let's say. And for the details and the particular limits for definite models, I'd refer to the coherent dark matter sensitivity paper on the archive. And that's basically all what I wanted to share with you. And I would like to say that Coherent has demonstrated the ability to measure coherent neutrino scattering with multiple target detectors at SNS, and we have an impact on the neutrino non-standard interaction, nuclear structure observables, some electroweak interaction parameters, and we are going to look at the accelerator produced dark matter phase space. So stay tuned, and thank you for your attention. You're welcome with the questions if you have any.
Thank you, Alexei. Questions? Okay, not seeing any. Let us move on to our next talk, which is Sterile Searches with Icarus from Christian Farnesi.
Hello, I suppose you can hear me, and
yes,
and also you can see my slide. Now I put there. Okay, full screen. So hello, first of all, I want to thank the organizer for the opportunity to present this talk here in this very interesting conference. So in this talk, I will shortly present the status of the T600 detector at Fermilab and some details about the search for the sterile neutrinos with this detector. So here you can see the Icarus collaboration that is presently composed by about 150 physicists, mainly from Italy and from the United States. So the Icarus T600 detector, with a total active mass of about 500 tons, is the first large liquid argon time projection chamber ever constructed. This detector, first proposed by Carlo Rubbia in 1977, is composed by two identical modules, and each module houses two liquid argon time projection chambers separated by a common cathode with a maximum drift length of 1.5 meters. Each TPC is made by three parallel wire planes oriented in different directions in order to provide a 3D reconstruction of each event collected in the detector. Behind the wire planes, there are also located photomultipliers that are used to collect the scintillation light produced by the particle in liquid argon, and this signal is the basis for the trigger of the detector. Icarus concluded in June 2013 a very successful 3-year-long run in the Gran Sasso Underground Laboratory. During this run, we collected events both related to the CNGS neutrino beam and to cosmic rays, demonstrating the 3D imaging and calorimetric capability of this detection technique. The run in Gran Sasso allowed reaching several physics and technical results, demonstrating the maturity of the RTPC technology that is really ideal for the neutrino physics. During this data taking, first of all, an exceptionally low level of the electronegative impurity in liquid argon has been reached, paving the way to the construction of larger detectors with longer drift distances, as the Dune detector. In addition, the events collected, both related to the CNGS neutrino beam and also to the atmospheric neutrino interactions, demonstrated the excellent detector performance, especially in the electron neutrino identification, and in the background rejection for the nu-mu oscillation studies. Thanks to this, with the events associated to the CNGS neutrino beam, we also performed a sensitive search for an anomalous electron neutrino appearance associated to the LSND anomaly, reducing the LSND allowed region for the possible existence of sterile neutrinos to a small region with c square to theta about 0.005 and delta m square smaller than 1 electron volt square. So in the previous slide, I mentioned the LSND anomaly. So as you know, different anomaly has been collected in last years and seems to indicate the possible existence of a fourth state of neutrino, the so-called sterile neutrino, that is characterized by large delta m squared of the order of the electron volt square and small mixing angle, driving oscillation at short distances. Presently, this sterile neutrino puzzle is still far from being fully understood. In particular, at the moment, there is no evidence of muon neutrino disappearance, And the most recent data have shown a strong tension between the electron neutrino appearance and the muon neutrino disappearance data. So in order to have a definitive clarification of this sterile neutrino puzzle, we need a new experiment that should be able to measure simultaneously the electron neutrino appearance and the muon neutrino disappearance, comparing the spectra that are collected in a near and a far detector that should be similar, with a good control of the backgrounds and of all the possible sources of systematic effects. The short baseline neutrino program at Femila satisfies all these requirements, and for this reason, it will play a very important role in solving this sterile neutrino puzzle. So the SBN experiment will exploit 3 liquid argon TPC detectors located on axis along the booster neutrino beam line. In particular, the near detector will be the SBND detector located at 110 meters from the target, and the far detector will be the T600, our T600 detector that will be located at 600 meters from the target. Here in this slide, you can also see the expected neutrino flux and the expected oscillation probability in the different detectors for the parameters that are summarized in the plot. During the SBN operation, the T600 will not only collect the BNB neutrinos, but we also collect neutrino interaction from the NUMI of axis beam, with a larger electron neutrino component and with an higher energy, around 3 GeV. And this will provide interesting information, in particular for the future long baseline project Dune. Here you can also find some numbers related to the expected rate in Icarus, both related to the BNB and to the NUMI beam. In this slide, you can see summarized the expected sensitivity provided by the SBN experiment, considering a 3-year long run, corresponding to 6.6 × 10⁻20 proton on target collected. So the fact that we use the same detector technology and that we start from the initial beam composition and spectrum that is provided directly by the near detector will greatly reduce the systematic errors in this analysis. In addition, thanks to the great capability to identify the electron neutrino events and to reject the backgrounds provided by the LRTPC detection technique, and thanks also to the simultaneous study of the 2 channels, so the electron neutrino appearance and the muon neutrino disappearance channels, the SBN experiment will cover much of the parameters allowed by past anomalies at more than 5 sigma significance, and so it can clearly help to clarify the sterile neutrino puzzle. Icarus at Fermilab will collect about 1 million neutrino interaction, and it will take data at shallow depth, facing more challenging experimental conditions with respect to the previous LNGS run. The T600 detector, in fact, will collect, will be protected from cosmic rays only by a 3-meter concrete overburden. So we expect to observe more than 10 cosmic muon tracks crossing the detector randomly with respect to the trigger time in the 1 millisecond drifted out window. These cosmic muons can, in addition, produce electromagnetic showers, and this can clearly mimic electron neutrino events. For these reasons, cosmic rays can become a serious source of background for the electron neutrino analysis. To face this new experimental condition, between 2015 and 2017, the T600 detector underwent an intensive overhauling phase at CERN before being shipped to FNAL. Important technological developments summarized here have been introduced in the detector while maintaining the already achieved performance. And in particular, in the next slide, I will provide you some more details related to the upgrade of the light collection system and of the TPC without electronics. So after the arrival of the 2 modules of the T600 detector at Femilab in July 2017, the detector installation went rapidly, and we are now essentially starting the commissioning. Here in particular, you can see some pictures related to the different phases of the detector installation. The 2 modules have been placed, as you can see on the top, has been placed inside the warm vessel during August 2018, and then all the fans have been installed. During 2019, we also completed the installation of all the new TPC without electronics, and we tested all the new installed mini crates. And also all the new cryogenic equipment has been installed, welded, and tested. The detector installation has been completed at the beginning of this year, and then between February and April, we filled the detector with liquid argon. And here in this plot, you can see, as a function of the time during the filling period, the level of the liquid argon inside the detector. In addition, we also started the liquid and gas recirculation that are fundamental elements, in particular to purify the liquid argon, and so to start to see soon very interesting events. So now let's go to some details about the upgrade that we have done to the T600 detector. So during the data taking at Fermilab, the light collection system will be used not only for the trigger, as we had done during the Gran Sasso run, but also to precisely identify the time of each interaction in the detector with a nanosecond resolution. And we want also to identify with the light signal the event position and topology to have a fast event selection. For all these reasons, the system has been improved during the overhauling phase. And now we have 90 photomultipliers per each TPC, with a total coverage of about 5%. The system has been completed in 2019 and essentially is now ready for the operation. And in particular, now we are starting to activate all the PMTs and to calibrate them at liquid argon temperature. And here, for example, in the plot on the bottom, you can see the measurement of the noise and the variation of the noise with time for 3 PMTs. So as you can see, we are starting to collect signal directly from the PMT installed inside the detector. Also, the TPC without electronics has been completely renewed, and it has been fully tested before the installation at Fermilab on a small liquid argon TPC detector installed at CERN. The most important improvements are related to the front end, the new front end, and to the faster ship time of about 1.5 microseconds that match the transit time between the wire plates. And so in this way, we can have a better identification of the physical signal connected on the wires. In addition, now we have a more compact layout. As you can see in the picture on the bottom, now both the analog and digital electronic elements are housed in a single board that is inserted in a new mini crate that is directly connected to the new signal feed-through flanges. In this way, we have a strong reduction of the space needed for the TPC without electronics. All these elements that I mentioned has been installed, and during the filling period, 10 mini crates has been continuously recorded in order to monitor the noise condition. And as you can see in the plot on the bottom, a steady increase of the noise level has been observed, and this is fully in agreement with the expected variation of the wire capacitance due to the increase of the level of the liquid argon inside the TPC. So during the Fermilab data taking, the T600 detector will be also corrected by the surrounded by the so-called cosmic ray tagging system that is composed by 3 subsystems, each one with 2 layers of plastic scintillators. This additional system will provide important information, in particular on the incident cosmic muons and also for the beam-induced muons. The few nanosecond resolution that will be provided by this system, combined with the study of the activity of the particle in the liquid argon so inside the detector, will allow measuring the direction of the particle via time of flight. And in this way, we can discriminate the incoming outcoming particles. And so we can remove, this can help to remove the backgrounds. As you can see in the picture here in this slide, the preparation and installation of the modules of the 3 subsystems is progressing rapidly. And at the moment, the commissioning of the 2 side walls is ongoing with Cosmics. So, in parallel with all the activities that are related to the that I just presented in the previous slides, also the reconstruction tools has been completely renewed. In particular, common reconstruction tools in the SBN detector will be fundamental to understand the detector-related systematics and their correlation across the near and far detector. So, starting also to the experience accumulated during the Gran Sasso run, the neutrino event selection and reconstruction is under development. And here in this plot on the bottom, you can see the first promising results. For example, you can see the capability to discriminate the electrons from the photons based on the study of the D over the X at the beginning of the shower. That is clearly a fundamental element in order to recognize the electron-neutrino events. In addition, we also demonstrate that the combined signal from the TPC, PMT, and CRT will play a very important role, a crucial role, in order to reject the backgrounds, in particular coming from Cosmics. So, summarizing, the T600 detector within the SBN project at Fermilab is expected to help clarifying the sterile neutrino puzzle by looking simultaneously to the appearance and disappearance channels, with a combined signal from 3 liquid argon TPC detectors. For the T600, the installation and the filling with the liquid argon has been recently completed, and the commissioning is starting. So Icarus will see soon new interesting neutrinos from booster, and the data taking for fields is expected at the beginning of the next year. So stay tuned for new interesting results from Icarus. Thanks.
Thank you. Any questions for Christian? And as before, you can use the raise hand feature if you'd like to ask your question verbally. All right. Well, thanks again, Christian.
Thanks.
And we will continue now to David Caratelli with Microboon's sterile search.
Hi, can you hear me and see the slides?
Yes, looks good.
Okay, great. So thanks for the opportunity to present the status of Microboon's search for low energy excess. I'm speaking here on behalf of the Microboon collaboration. So the motivation for this talk is the observation by the mini-boon experiment of an excess of electromagnetic activity at low energies in the boosted neutrino beamline. So this is referred to as the low energy excess, or LEE for short. And it's part of a broader context of short baseline anomalies. There's little ambiguity as to the fact that this excess exists, but there's remaining questions as to the origin of the excess, and specifically whether it's induced by electron or photon electromagnetic showers, something that mini-boon cannot disambiguate. And finally, there's also the greater interest question whether this is caused by new physics. So the Microboon experiment was built specifically for the purpose of addressing this question, and it relies on the liquid argon TPC technology, which we've heard a lot about in this session, to answer this question. And you can see a demonstration of the ability of separating electron and photon signals with our data from high energy in this plot on the bottom, with electrons, as an example on the left, separated from the photons, where you see an example here on the right. Microboon's analyses have come a long way, and we've been collecting data for 5 years. What I'll be presenting is the status of the first low energy excess searches using 3 years of data. To get to this point, we've had to achieve several milestones, including stable operations of a large detector, developing a lot of tools in terms of automated reconstruction and detector modeling, understanding and measuring neutrino-argon interactions, and of course, developing analyses that are sensitive to searching for electron and photon signals in our data. We're currently at the stage where we're validating our analyses and getting ready for our final box opening. And it's important to note that many of the milestones along this line are kind of pioneering work from Microboon in terms of developing the technology to make it able to perform precision neutrino physics. So when it comes to studying the low energy excess observed in mini-boon, there's a whole range of literature that one can choose from in terms of finding a model or a phenomenology to test. To keep things simple, the first generation of results that Microboon is addressing is looking at 2 models in particular. And both of them are developed by taking the mini-boon excess from their published data, unfolding it through smearing matrices to recover under 2 hypotheses unexpected event distribution. Under the electron hypothesis, this is a scaling of our intrinsic electron neutrinos, which populates events at the lowest energies. And under the photon hypothesis, this is a scaling of neutral current delta radiative events, which instead leads to a roughly 3 times scaling of the standard model process. So these 2 models are those that we're testing and that current analyses are being benchmarked against. You can read more about these models in this note here. There are multiple analyses in Microboon trying to get to the bottom of this question. And in the interest of time, what I'll try and do is highlight common aspects of them and, when appropriate, briefly introduce the key features of each analysis. There's many more details on these analyses than what I can present here, so I'm providing references with public notes for the various analyses that I'm going to discuss, and you're encouraged to go and look at those details if interested. So the first common step to all analyses in Microboon is the need to reject cosmic rays. We're a surface detector, which means that we're inundated by cosmic rays traversing the detector volume. We use off-beam data in order to perform a data-driven assessment of our cosmic backgrounds. And to make a long story short, in the context of these analyses, we start with having collected about 500 million with a B off-beam triggers, and through the use of scintillation light and pattern recognition, achieve a background expectation of less than one off-beam event for the final distributions that the analyses have developed. So quite a feat in terms of cosmic projection. Another important step is detector modeling. You can see here an event that Mark showed before. It's a pi0 event with a proton. We need to make sure we model our detector response accurately for this analysis. And we're able to do so we're able to test this by using our own data. So you see an example of our reconstructed pi0 invariant mass up here with good data Monte Carlo agreement and good agreement with the expected pi naught mass. And here you see a validation of our proton data showing the expected dx versus residual range with the data on top of that. All of this is possible because of really several years of development in terms of detector modeling, signal processing, and calibrations, which all allow us to achieve a good understanding of our detector response and consequently precise measurements of particle kinematics. So from detector to neutrino interactions, this is another important part in performing this analysis. We need to be able to have an accurate modeling of our neutrino-argon interactions. And of course, this is a challenge in all neutrino experiments. For us, it's particularly true because of the sparsity of neutrino-argon interaction measurements and the relatively few samples of data constraints for interactions at cross-section measurements at low energies, which is the region of interest that we're studying. So here we leverage 3rd generation of microballoon analyses, which use progressive improvements on simulation, reconstruction, and analysis tools, as well as state-of-the-art neutrino interaction models. We're using GenieV3 together with tunes to the latest and greatest, most relevant data that's out there. And putting these two things together, we're able to achieve low detector systematics, lower than what we had reported previously, good reconstruction tools capable of 4 pi measurements, and importantly, a robust neutrino interaction model with good data Monte Carlo agreement in the phase space that we are able to measure. Having a model that matches our data is only one part of that, part of this analysis. Another important step is being able to constrain our uncertainties. And that the reason for this is that backgrounds to these searches and uncertainties on those backgrounds drive the sensitivity to new physics. So what we do here is measure sideband distributions with high statistics in order to constrain backgrounds to the photon and electron channel. In the photon channel, the measurement is on the neutral current pi0 side, and you heard a lot about this from Mark earlier. And on the electron side, what we do is we measure high statistics muon neutrino interactions and leverage correlations in flux and cross-section with the electron neutrinos to constrain our intrinsic electron neutrino prediction. And just for demonstrating the idea here, I'm showing a correlation matrix which shows the correlations between, for example, the muon events and the electron events, looking at our flux uncertainties. So in the second part of the talk, what I'll try and do is just give us a flavor for where the low energy access analyses are right now in microballoon. And let me start with the photon side. So we have a single photon LEE search, which selects final states with one single electromagnetic shower, photon-like shower, and 1 or 0 final state protons, consistent with MINErva's excess observation. The search tailors a specific channel, which is the decay of delta radiative events into a radiative photon. And as mentioned also by Mark, this channel benefits significantly from a constraint of its backgrounds in the 2-photon channel with preliminary results shown here for the invariant mass of these neutral current pi0 events. This analysis will provide the most stringent constraint on the standard model neutral current delta radiative decay in neutrino scattering data. And as currently designed, is capable of excluding the radiative delta decay interpretation of MINErva's LEE hypothesis at greater than 95% confidence level. Now let me go and describe the electron channel searches, and there's several of them, so bear with me as I present the features of each one. So one of these analyses is focusing particularly on CCQE-like events. So using the similar reconstruction definition as for the MINErva analysis, but with the added benefit that in liquid argon, we're able to see the protons in these interactions. And what this analysis leverages is the fact that using both the proton and electron kinematics, the event can be over-constrained and the selection of CCQE events can be really tailored and quite pure. The analysis leverages several novel reconstruction techniques, including several deep learning methods. And you see here a validation of some of these two-body quasi-elastic-like scattering kinematic consistency checks on some of the high-energy data for our analysis. A second measurement is trying to be more inclusive. It looks at, tries to measure electron neutrinos in a broader topology range and specifically looking at any number of final state protons. You see here the expected distribution of electron neutrinos in green with the expectation for a possible LEE-like signal in orange for the channel with one or more final state protons and the channel with 0 protons at the bottom as well. The thing I'll highlight here is the high purity in electron content that's obtained. So if you remember the mini-boon result, as you go to lower energy, you start boosting those photon events. And here really those backgrounds are under control thanks to the additional PID that the detector provides. The final search is based on the wire cell tomographic imaging methods. While is earlier in its development phase, is promising in its ability to achieve higher efficiency compared to current searches and aims to perform an inclusive search. You can see here on the bottom preliminary distributions of data Monte Carlo comparisons from the muon and electron neutrino channels. So where are we? We're at the status where we're validating with sideband and limited open data sets the robustness of the analyses. You can see here an example with a small open data set, the signal region for the photon search. And on the right, you can see for 2 of the electron searches, validations in the high energy range of the electron search for data and Monte Carlo comparisons. So we're at the stage where we're seeing promising results indicating robust analyses and are nearing a full box opening. So to summarize, Microboon aims to address the origin of mini-boon's low energy excess anomaly, shedding light on a significant anomaly in short baseline neutrino experiments. We're leveraging multiple years of development in analyzing liquid argon TPC data and performing complementary analyses to be sensitive to new physics at low energy. These analyses are now mature and are being validated with sidebands. The first generation of analyses is getting ready for a final box opening. So whether we see an electron-like signal or photon-like signal is not an answer we have yet. But if you've made it this far in the session, you have the stamina to wait a bit longer for that result to come out. So thank you.
Thank you, David. Any questions? All right. Thanks again. And we have one more talk about a new physics search with NA62 from Evgueni Goudzovski.
Hello. Shall I share my screen now?
Yes.
Okay. Okay, do you see it now?
Yes, looks good.
Okay, thank you. Well, thanks very much for staying so long into the session to listen to the searches for heavy neutral lepton production at the NA62 experiment at CERN. So I will briefly introduce the CERN count physics program and the NA62 experiments. Then I will talk about the search for production of heavy neutral leptons in 2 body decays of the charge counts with a positron and a muon in final state. I will compare our results to the results from other production and decay searches, and I will proceed to the summary. So CERN has been hosting a counting experiment program for many decades, actually. And just in the last 20 years, it's been home to 5 distinct count decay experiments. The most recent of them is the NA62 experiments that I'm going to talk about. all these experiments are housed in the north area, in the ECN high intensity hole. So they make use of a 400 GeV protons extracted from the SPS accelerator and being extracted into a target to make a secondary count beam, high intensity and high energy count beam. So the main goal of the Na62 experiment, which is a very high intensity K plus decay in flight experiment, is a measurement of the K plus to pi nu bar decay to a 10% precision using the decay in flight technique. And actually, just a couple of hours ago, there was an announcement of a new result coming from the full run one data set presented at the flavor physics session. So the Na62 experiment looks in the following way schematically. So the primary SPS protons are used to produce a secondary high intensity charge count beam, which then enters a large vacuum tank of a volume of a few hundred cubic meters. And this is where the decays of the counts occur, which are recorded by the detectors. So the detectors are composed of two beam trackers. There is an upstream beam tracker for the incoming counts, and the downstream tracker, which is a straw tracker immersed directly into the vacuum to make a very good resolution and the small non-Gaussian tails to detect the outgoing products of count decays. Then there are two Cherenkov detectors to tag the count and identify the downstream tracks to a precision well below 100 picoseconds. And finally, there is a hermetic system of photon vetoes, which consists of 4 different types of colorimeters and a hadronic colorimeter and a muon detector. So roughly 1 year of operation corresponds to 10 to 18 protons of target and a few times 10 to 12 count decays in the vacuum tank recorded. So this is a high intensity experiment. Okay, so let me move on to the Na62 data collection. So we have completed our run 1, which consisted of 3 physics runs in 2016, 17, and 18. So we've been ramping up the number of protons on target per pulse, per SPS pulse. And in total, we have collected about 6 times 10 to 12 useful count decays and about 2 units 10 to 18 protons on target. And we are restarting in 2021, going 1 step up in intensity. And we are planning to collect an even larger data set. So now let me move on to the main subject of the talk, which is a search for heavy neutral lepton production. I'm going to talk about searches for production with a positron, and that's a result published about a month ago. And I'm also going to present a preliminary result on searches with a muon based on a partial data set. So, well, just to introduce the dark fermions, there is a generic possibility of a number of sterile neutrino mass states, so that the flavor eigenstates are linear combinations of more than 3. The mass eigenstates are linear combination of more than 3 flavor eigenstates, or vice versa. And this kind of idea is motivated largely by the relation to the neutrino mass generation. And one of the popular theories on the market is the neutrino minimum standard model, which is an economical theory which accounts for neutrino masses, oscillations, baryogenesis, and dark matter by introducing just 3 heavy neutral leptons, of which 2 are expected to be at the GeV mass scale. And in terms of the coupling and the mass, this is roughly speaking the range which could be probed by both decay and reduction searches. Well, now thinking about production of heavy neutral leptons in count decays, in charge count decays, this kind of 2-body decay, right? Count going to a lepton and a heavy neutral lepton. Well, the rate of this decay is a product of 3 factors, as was known for the last 40 years. That's the branching fraction of the standard model decay times the kinematic factor times the square of the mixing element of the extended neutrino mixing matrix. So actually, numerically, the product of the branching fraction and the kinematic factor is of the order of 1 over a large part of the available HNL mass space. And if we look at the blue curve here, well, actually the kinematic factor reaches about 4 for a neutrino mass of about 200 MeV. So actually the production of a heavy neutrino is enhanced with respect to the production of a standard model neutrino. Well, this is due to the helicity suppression, which is relaxed for a heavy neutrino. And this effect is even more dramatic. Actually, it's a factor of 100,000 enhancement for the positron case, because the helicity suppression is reluctant. Of course, the standard model helicity suppression is very strong. Okay, now let's move on to the Na62 data sample. So the data sample effectively corresponds to about 3 × 10⁻12 kaon decays in the positron case, and about 4 × 10⁹ decays in the muon case. Well, the muon sample is much smaller because the muon sample is heavily downscaled. There is a downscaling factor of 400 used for the muon case. So how do we look for production of a heavy neutral lepton? We reconstruct the squared missing mass, which is a difference of the 4 momenta of the incoming kaon and the outgoing charged lepton squared. And for the standard model, we can see spikes at 0 missing mass. So we observe about 3 million helicity suppressed K to E nu standard model decays, which is seen on the left-hand side of the slide. And we observe about 1 billion of standard model K to mu nu decays, which is a major decay mode with a branching fraction of 60%. Now, to look for a heavy neutral lepton, we are looking for additional spikes over the continuous missing mass spectrum at large values of missing mass. Okay, and we can see immediately that this kind of search is actually dominated by the background. So in particular for the positron case, the dominant background is due to kaons going to mu nu with a muon decay in flight. So we're effectively seeing here a system of 3 missing neutrinos, which have a continuous mass spectrum, starting from 0 and going all the way to the kinematic endpoint. Now, in the muon case, the situation is better. The background is small, and actually the background is dominated by radiative decays of a kaon into muon, neutrino, and a photon. Okay, one important parameter of merit when looking for heavy neutral leptons is the mass resolution. And indeed, well, the mass resolution depends strongly on the HNL mass itself, but typically for masses of a few hundred MeV that we are searching for, the typical mass resolutions are of the order of 1 MeV. So actually, it's a fairly good mass resolution, which means that also the background is kept under control because the background is proportional to the mass resolution. Okay, now let's move on to the acceptance and single event sensitivity. So the acceptance for a kaon decay into a charged lepton and a heavy neutral lepton is presented on the left-hand side of the plot. And we can see that for the muon case, the acceptances are typically of the order of 25–30%, almost all the way to the endpoint. While for the positron case, the acceptances are of the order of 10%, and there is a non-trivial mass dependence, and this is due to the way the trigger of the Na62 experiment operates. So basically, it removes part of the signal for lower HNL masses. Now we can define single event sensitivities, which is just 1 divided by the number of kaon decays and acceptance for the branching fraction. This is the branching fraction which corresponds to observation of a single signal event. And this turns out to be of the order of 10⁻⁹ for the muon case, and of the order of 10⁻11 or even 10⁻12 for the positron case. But unfortunately, the backgrounds are dominated by, the analysis is dominated by backgrounds, and therefore the actual limits obtained on the production are not as good. Well, the single event sensitivities for the mixing parameters are also of the order of 10⁻⁹ and 10⁻12 correspondingly for the muon and the positron channel. Okay, now let's look at the results from the search. So, well, on the left-hand side, the blue curve is the number of observed signal events in each of the heavy neutral lepton mass hypothesis checked. And one could see that these are very large numbers of the order of 10 to 5. So this is clearly a background limited measurements. And then the red curve here is the actual upper limit at 90% confidence level on the number of signal candidates compared to the expectation and the 1 and 2 sigma bands on the expectation in the null hypothesis. So one can see that these limits are of the order of 10⁻�3. And on the right-hand side, it's the same kind of upper limit on the number of HNL emission events as a function of the mass hypothesis compared to the expectation. one can see that the observations are within expectation, so we don't see any spike, except for one point, which is 3.6 sigma away from the expectation. I will talk about it in a second. So these observations could be converted into the upper limits on the branching fraction of k to L mu decay. And the branching, these upper limits are of the order of, 10 to minus 9, a few units 10 to minus 9 in the positron case, and they're of the order of 10 to minus 7 in the muon case. And I've already mentioned that there is one specific mass point for which we observe a maximum local significance of 3.6. However, if we account for Lux elsewhere effect, this leads to a global significance of about 2.2. So we conclude that we don't observe any HNL emission. Now, well, I'm going to this busy plot, which is a summary of our results in comparison with other HNL production searches, okay? So the red curve here is our final result for, in terms of the upper limits on the mixing with the electron. So we can see that the limits are of the order of 10 to minus 9 for in a mass range from 140 MeV to about 450 MeV. And we can see that this actually improves and saturates the bound from Big Bang nucleosynthesis, which is here as a dashed line. And the black line here is our new limits for the muons. And we can see that we approach the Brookhaven E9 for 9 sensitivity, and we extend the limits at the level of 10 to minus 8 to about 380 MeV. Now, finally, let me quickly compare our results to the results from other decay and production searches, just to put this result into a context. And this plot here is actually a PBC, a physics beyond collider plot, produced in November 2019. So this shows the exclusion for HNL production. So this is an exclusion in terms of the coupling as a function of the assumed mass of the heavy neutral lepton. And this is a summary of both production and decay searches. So we can see that, well, this is in particular in the assumption of electron dominance. And we can see that the Na62 result improves on the decay search and the classical decay search from the PS191 experiment at CERN, which is quite an old experiment. It's almost 40 years old now. Then this decay is complementary to the search for HNL decays at T2K. You see there is complementarity in terms of the mass range probe. And finally, the Big Bang nucleosynthesis allowed range is excluded up to a mass of about 340 MeV. Now, this brings me to my conclusions. So the Na62 experiment at CERN is a count experiment which collected about 6 times 10 to 12 count decays in flight during its run 1. And I presented the results on heavy neutral lepton production with a full run 1 data set. And the limits obtained on the mixing parameters are of the order of 10 to minus 9 for a broad range of HNL masses, kinematically accessible in the positron case, and of the order of 10 to minus 8 in the muon case. And well, there is an interesting improvement and complementarity, especially in the electron case, as I have shown in the previous slide. So thanks very much for your attention. That's all from me.
Thank you very much. Any questions? All right. If not, I believe that concludes the session. And thanks everyone for sticking around. It was certainly quite a marathon. Thanks again to all the speakers.
Bye.
Bye-bye.